Great. All right, everyone. So once again, PBR, physically based rendering, PBS, physically based shading, same principles, just called something a little bit different. Um, it's going to use, if you pick up a textbook on PBR, it's going to be about this thick, and it's going to cover everything you can do with it. And Unity is going to have a small subset that they work with. And we'll talk a little bit about what PBR actually means and why it's pretty much the standard these days for creating any kind of asset or content and how you render scenes in any typical title unless you're going for a very stylized effect, like a toon shader or the Street Fighter game, for instance. The new ones at least have a very unique feel, so you might not use these for them, but it's meant to more accurately represent how lighting interacts with an environment than the models we saw before, the ambient, diffuse, and specular ones. And then, of course, we're going to talk more about the surface shader. Surface shader is important to understand. It's a Unity-specific shader. Hold on one second. I want to make sure I have the chat available as well, because sometimes I miss things. There we go. So the surface shader is not something you're going to find in other applications. It's a specific stage that Unity created within its larger pipeline that you insert your code into. So it's not the vertex shader or the fragment shader, and you're not going to find it on any GPU implementation. It's instead something that Unity provided so that you would be able to benefit from all the code they already have without having to reproduce it. For instance, well, you know what, we'll talk more about it as we go through the lecture. No reason to talk about it all just quite yet. So the first thing I want to say was, for those of you who don't listen to me and think I don't know what I'm talking about, I am a certified expert programmer by Unity. I just got this notice last week. It's the first expert level certification that they have for programming, and it lasts about 2 years. I wanted to bring it up because it was an incredibly difficult exam, actually. I'm not endorsing certification anyway. It's expensive. I happen to get a low cost certification because it's the first time it was ever done, and they used my answers and everyone else's answers who took it to determine what the grading was, the criteria for passing or failing. So luckily I was able to pass. But they have multiple tiers and they all have different price ranges, and obviously the more higher tiers are going to cost a little bit more. But if you are going to be using Unity in the future, if you want to be a freelancer and you don't have many projects under your belt, the certifications are a great way to just, pop it on your resume and say, look, I know what I'm talking about. I don't need to have, X years of experience. Although I will say the expert level certification, it says you should have 5 years of Unity work experience, and that's real work experience. That's you at not as a programmer sitting at a desk being told what to do, but someone who's actually determining all the steps, the higher end pipeline, how things work. Because the questions were meta questions. They're not like, what's a vertex, what's a vector. They are very high level stuff. Very interesting. I can't obviously say what any of them were, but I experienced several of those questions doing active research projects at Rowan University. Is kind of the level that they're at. So other industries coming to us, to Rowan, to do research in areas that haven't been figured out yet were the levels of questions on that higher tier of certification. So just wanted to let you know that it's out there, that this is something you can try to do if you want to. And of course, they try to sell you material on learning how to get certified yourself, or that is study prep material, and that's probably how they make their money. I didn't do anything like that. There wasn't any prep material for the one I took because it's new. But if you're considering it, I could talk to you about it and let you know a little bit about what I experienced. Now that I've passed this one, I'm probably going to get all of the expert certification level tier stuff. There's a technical artist in shading effects. Pretty confident I could pass that one today. Then there's technical artist in rigging and animation. That one's going to require a month or so of studying before I'm ready for that one. But yeah, it's an interesting thing. And if you want it and you feel like this is something interesting for you, I'll talk to you in a little bit after I finish my dissertation. And if I'm looking for a job, I'll let you know if it actually helped me in any way if you're interested. That being said, let's dive right into physically based rendering, or physically based shading as Unity puts it. So the reason I say PBS is because if you're doing searching online, which you should be when you have questions, you're going to be writing PBS when you're doing your Unity search results. In the past lecture, we discussed how light and different techniques are pretty much there for you to work with inside of real-time engines. We worked with one of the simplest lighting models out there, and it's been around for decades, at least 30 or 40 decades probably. And those are diffuse, ambient, and specular terms, and they're pretty easy to calculate. Ambient, of course, was just whatever you want it to be. It's just an additional value. Then we had diffuse, which was a dot product between the normal vector and the light direction. And then, of course, finally, we had the specular term, which was the most complicated one. And that's mainly because you potentially needed to calculate a new vector, whether that's the half vector because you're going with Blinn, or if that's the reflection vector if you're going with the Phong lighting model. And then you need to, of course, raise that to an exponent, which is the shininess value, which will determine how wide or how tight the silhouette is, or not the silhouette, the specular highlight, that little white glossy mark on the surface is. So those are very easy. Now, physically based rendering, specifically, it's referred to as the standard shader inside of Unity. And you are going to get some contradictory information these days. And the reason for that is mainly because it has to do with the pipeline. We're supporting 2019.4.x. That's what we're doing. With 2020 and 2021, Unity is making changes, and they already have started rolling them out. Things called the universal pipeline or the highly configurable pipeline, and so forth and so on. And the idea is they're trying to open up and unlock more of the existing pipeline. And it's taking so long because it's not an easy thing to do. To make an entire rendering pipeline flexible and making it easy enough to use so that you don't need to understand everything about the engine is a pretty daunting task, and make it reliable and work on every platform that Unity supports. So you can understand it's going to take them some time to get all the kinks out of it, which is why we're focusing on the standard model, which is built into Unity. It's going to stay built into Unity, and it's really, really great when you're just starting off to work with it because it's very extensible. You can add all kinds of features you want to and pretty much make it just as good as some of these other pipelines. For now, eventually technology will move ahead and this pipeline will age and you'll have to move on. But for now, this is a great stepping stone from those ADS stuff to PBR and then finally to the future, which is all sorts of interesting stuff that unfortunately we don't get to cover yet in this class. So the standard shader, as I mentioned, is built in. It's great for hard materials. What it's not great for, though, are soft materials or molasses or honey or skin or hair or anything like that. Materials where light goes through the surface and, as we mentioned last time, has subsurface scattering is where you have problems with this shader working right. And many times you'll have extensions or additional passes made with these same shaders, but they try to add some of the effects that are missing. However, what you need to understand, though, is that PBS still has an ambient, diffuse, and specular term that gets calculated. They're just calculated in different ways. So some of the things that PBS supports is the principle of energy conservation, the idea that the energy coming in, that is the energy coming, excuse me, let me reverse that. The energy coming out should not be greater than the energy coming into the system. So the light comes in, strikes different objects, correct? Hits them and is converted to heat. Maybe it's converted to other kinds of light or different wavelengths, depending upon how light interacts with, the electrons. Maybe it strikes something there, does something weird, and makes a weird particle. What are they called? The Feynman diagrams, virtual particles, that's what it is. It creates maybe something different. Either way, energy is coming in, and you should always be getting less energy coming out of the system because it's being, changed and modified. That being said, there's also Fresnel reflections, which we're going to talk about briefly. That's an interesting kind of reflection based upon the grazing angle. That is how you're viewing the scene and how it will illuminate different parts of the object. And then there's things like surface self-occlusion, that is a surface blocking itself and how it should be illuminated, and many more. Now, one thing you need to know,
Quick question.
I mentioned this at the beginning of the class, but most likely you've kind of ignored it and you really haven't looked at it, but that was the universal rendering pipeline in the HDRP, the high definition rendering pipeline. And we're not discussing
Quick question,
that.
George.
Excuse me?
I had a quick question for you.
Sure, what is it?
On the last slide, what about the standard surface shader makes it better for harder materials instead of softer ones?
The standard shader itself is only meant to approximate light that strikes the surface and then bounces off. It is not meant to replicate the effects of light when it penetrates the surface and undergoes subsurface scattering. And of course,
Hence,
the best indication of that
gotcha.
is to look at don't look directly at a light. Never do that. even though our president did it. Don't do it. It'll hurt your eyes. But put your hand in front of the light and then look at your hand through the light source, right? You'll notice your hand glows, right? Or put a flashlight up against it. That kind of stuff is what it can't replicate. And that's what gives you the
Okay.
lifelike nature of human skin itself, because it's interacting with the cells, the plasma, the blood, the veins, everything. So when you look at your hand, remember your hand is a little bit transparent, right? You can see features under your hand and into your skin, not terribly deep, otherwise it'd be kind of gross, but enough so that it does cause an interesting effect, especially that halo effect or the warmth, the redness of the hand, right? That you get when you have extreme lighting, especially on the ears or the nose or the lips, right? Because those are thin, those are cartilage, especially. Not the lips, obviously, but that's another area where it can become pronounced. And a lot of times, what you'll end up with is if you use a standard shader on a person, they look like they have been covered with, makeup, tons and tons of makeup, and they no longer look lifelike, and that's why it's great for architectural rendering. It's great for solids, metals, things like that. But anything where the light actually has to go through it or interact with it, it's not the best approximation. And remember, it doesn't approximate any kind of ray tracing-esque elements. So it won't do scattering, it won't do prisms, it won't do anything like that when you're dealing with transparency either. It will not do, where the light will go through and then bend and then come back out and bend again. So if you have a cup and you put water in it, it will not replicate the bending of light as it passes through a new medium. So those are all the kinds of effects that this won't help. But just by adding the fact that the energy coming out has to be less than or equal to the energy coming in really helps the system out and makes it much more physically correct, physically proper than what you get in the old algorithm. Because the old algorithm, you could plug in whatever you wanted to, right? You could plug in any value for ambient, any value for diffuse or specular, raise them, lower them, it doesn't matter what you wanted to do, and really blow out your scene and just completely destroy it. Here, there's a balance being kept. And because of that balance, you need to be more aware of the strength of your lights, right? You're not just going to blast a light as high as you can with its maximum intensity, right? Because that's going to have repercussions on the entire scene at that point. So things become much more realistic. You start talking about units of light, like lumens or candela, or all these different ones that I will say I was very not familiar with when I started, and it takes some time to get used to them, because before I was just like, all right, intensity, crank that sucker up all the way to the top until it looks right. But now you got to think, okay, how bright is a true incandescent light bulb? Because if I'm going to have this in a room with a monitor, I want the monitor to be a soft light, but the light above me to be a harsh, hard light. But I need to balance them as well, because if the character brings out a flashlight, that needs to have the proper value so it's not super bright and blows everything else out. You can, of course, wing it and adjust them over and over and over again until you get the right feel. But it's just a lot easier to go online and look up what the actual value or intensity of these objects should be and use them inside of your rendering software. And that's actually what you see in a lot of architectural rendering pipelines. 3D Studio Max and so forth have all of these things built into it. And all you do is you say, all right, plug this kind of light bulb in here. It's all set up, what the wattage is and so forth, and it will replicate the lighting relatively faithfully to what it should actually be. So, rendering paths. I needed to bring this up because we need to talk about forward and deferred rendering, because it's going to start popping up every now and then, and it does have implications to what kind of shaders you can write or what features and functionality you have access to. This is a little high level, but we're just dipping our feet into it, all right? And the idea behind this is you'll know just enough information to choose one or the other depending upon what you're doing. Because choosing this early can have consequences later on with whatever project you're working on. But anyway, what I'm talking about does not count with the universal rendering pipeline, the high definition rendering pipeline, or the old legacy stuff. This is the built-in pipeline. It will be around for a while. Any projects you're currently working on will still incorporate it. And if you are going the indie route in your future, teaming up with a couple friends to make a game, this is something that will be around long enough and is fully supported long enough to where you could release your game if you just started it today and be fine. So don't worry about it. What a rendering path is, it's the series of operations that are behind the scene, that are kind of hidden from you, that end up figuring out what the lighting and shading of the scene should be. And what you don't think about first is that, well, there are options. You don't have to use the algorithms that are provided to you. You can come up with your own. Of course, doing that means you need a lot of technical know-how. But still, that's how we get better at things, right? People try new things, they fail, but then someone finds something that might work better. Each camera you have can have its own rendering path. And the two types are right now forward and deferred rendering. And I actually remember where forward rendering wasn't even a path, it was just the way you did everything. It was the pipeline, period. Deferred, and I can't remember, I think maybe 10 years ago is the first time I heard about deferred rendering, is interesting because the idea is it does all the processing and kind of stores it all. And I'll get more into it. But the important thing to understand is you can go to the graphics window in your project folder in your project options and choose one of these different pipelines. Or if you want to, you can do it on a per camera basis. And the reason for that is because maybe you have a cinematic scene. Maybe you have something where certain features aren't necessary, but you want it to look really amazing. Maybe you've got 100 different candles lighting up a cultist's, bedroom, and you want each of those candles to be accurately portrayed around the person. I can tell you right now, one of these paths will not do it. The other one will. However, if you're in an aquarium and maybe there are panes of glass in front of panes of glass and you have to see through multiple objects, one of these pipelines will support the transparency, although you'll have to do a lot of work to get it to work properly. The other one will not support transparency at all. So there are some big differences between the two, and you need to know these to make a choice in the future. So the first one we're going to talk about is the forward pipeline. Now, the forward pipeline is the pipeline, if you're as old as I am, because it is the way we did things for the longest time. You didn't have another option. It was researchers who came up with the deferred pipeline later on. But the idea is that you have, it pretty much mimics the path we've been learning so far in terms of how things are processed, where I talk about how we process vertices and they go into the scene, and then we process each light, and each light lights up the different parts of the vertices, and we calculate each and every single individual one. However, it's quite tedious to calculate each light, because if you think about it, what do we have? We have a vertex shader, we have a fragment shader. You can do lighting calculations in either, but either way, you have n number of lights in your scene, which means you now have a loop inside of your shader that has to run n times. So all those calculations that you've been doing right now, imagine now you have to multiply that by n, and you can think about how much longer it's going to take. And because of that, there are limitations to the forward rendering pipeline. What you need to understand is that every single light in your scene by default has a property. If you look at a light in the inspector, it has a drop down. And it's the render mode that determines the light's priority. And that priority is used by the forward rendering path to determine how it lights the scene, if at all, really. If it's set to not important, which I believe is the default, the light may be rendered per vertex, or it might be rendered through something called spherical harmonics, which I mentioned before. We'll talk about that a little bit, but don't worry too much. Let's just say that is a way of grossly simplifying the lighting's effects on the environment and storing that in a 27 floating point value that is used similar to Fourier series, right? So with that, you end up truncating it, right? You cut off a certain number and you throw away the high frequency information. Well, you have a certain number of these bands you use, and those bands are all low frequency information. So because it's low frequency information, spherical harmonics are actually very bad if you have tightly changing light sources, but they're great if it's gradual changes from one place to another. Next up is if it's not important, so it's either per vertex or spherical harmonics. Next up is brightest direction light is per pixel. So you have a directional light in your scene by default that is added into your scene. And the brightest one that you have in your scene is always going to be rendered per pixel, flat out. That's the way it does it. So the first one you have that's the brightest one is the one that's going to get the highest quality. And actually that's all done in one pass, which is interesting. Next up are the per pixel lights. You can specify them to always be per pixel, but the thing is, even if you had 100 lights and you specified all of them to be per pixel, Unity is going to figure out a way of making that so it doesn't destroy the rendering performance. So in your settings for your scene, you get to specify how many per pixel lights you support in the graphics window. Typically, that's around 4 or maybe 6 or maybe a little bit higher. You can specify higher if you want to, if you got the system that can push it out. However, you're not going to want to do that usually. So any lights that are left after it hits that cap are going to end up becoming per vertex or spherical harmonic values instead. And if you don't hit that cap and it still has more per pixel lights, it's going to go iterate through your lights and it's going to figure out which one's the brightest, which can also has to do with distance, mind you, and it will render those. So depending upon your scene, like I mentioned that scene with a cultist and 100 different candles, well, it's not going to render 100 candles, right? It's going to render maybe if you have a directional light, maybe there's a window, right, that's covered up with a Megadeth poster or something, right? And there's some light streaming through. Maybe you have a directional light outside. That would be your primary directional light. And then you would have your maybe 6 of those candles, the ones closest to the camera, the perspective, would be well illuminated, per pixel illuminated. But then all of the other candles are going to end up being per vertex or most likely all spherically harmonics calculated instead. So because of that, you got to understand you just can't throw lights everywhere. Okay, Unity's smart. It will figure out the optimum lights to turn on based upon distance and intensity and so forth. But still, just throwing lights around the place is not what you want to do in the forward rendering pipeline. Here I've got a red box over here, and the important thing here, let's get this pointer out again. And what's important to understand, let's see, let's pick a color that'll show up. We'll do green, we'll do Christmas colors, green, red. In the forward pass, you actually have 2 passes. So you think of it, it's called forward pass, singular, but in reality, it's broken down into multiple passes. And actually, it can be many more than 2, actually. The base pass does your per pixel calculations for the directional light, and then it does all the spherical harmonic stuff, any light mapping, that's the light baking we were talking about, any of the ambient or emissive maps, so that's where textures have emissivity, and then any shadows. The additional passes, and this can be as many passes as you have per pixel lights, right? So if you had 6 per pixel lights enabled, not counting the directional one, this would be another 6 passes being done. That's another 6 render passes, okay? And the per pixel lighting in that case would be calculated for each one. Now, one thing to understand is that typically these don't have shadows by default, according to the documentation. However, it seems like the more recent versions of Unity have relaxed that requirement a bit because you'll get shadows on these regardless. An interesting thing too is that the spherical harmonics, I talk about them. What's interesting about them is apparently they're almost free to compute. That is, it doesn't matter if you have 1 spherical harmonic object or 100 of them in your scene. The way they're processed on the GPU, and I'm not exactly sure, I got to really look at the math, but I'm guessing they're probably summed, right? Or something like that is being performed where they're all calculated at the same time and it's essentially free. So there's a huge limitation with that though. It does not support cookies, which are, I think I showed the example of the weird lights with a smiley face in the other lecture, normal maps or anything like that. But it is free. So do understand there's a time and a place for spherical harmonics, and I would recommend low background lighting, features that are further away, not close-up stuff. That's going to be the best place for them. Now deferred. Deferred is really interesting. It's going to make it so that the loop that I was talking about before isn't as bad. So instead of every object needing to iterate over every light that is nearby and processing it, and potentially, remember, one object might be in front of another one, and maybe it was rendered, in which case you did a lot of processing on a lot of lights, and you never got to see anything from it. Deferred is actually going to render the entire scene beforehand and store it in something called the G buffer. G stands for the geometry buffer over here. And the G buffer isn't just one buffer, it's actually a series of buffers, and it can be more than what's shown here, depending upon additional pipeline features that are added to it. But what's interesting here is that each of these buffers are just typical pixel information. If you think about it, we have ARGB 32, that's alpha RGB, 32 bits total, so 8, 16, 24, 32 for each one. One buffer holds diffuse and occlusion information. So what's diffuse? Well, that's the diffuse value that gets calculated for that particular surface, right? Another buffer is going to hold, oh, by the way, that diffuse would hold up the entire RGB value of it, and the occlusion would be the alpha. Specular is also a color term. It can have color, so it would also fill the entire RGB value and the roughness. Why does this matter? Because in the fixed pipeline, when you are processing your pixels, right, you are putting out a final color. Not so with a G buffer. You are putting out almost like the contents of the fragment shader to multiple buffers, so that when you've processed the entire scene and you have these buffers of information, each one having different things, you can look at them all at the same time. And instead of worrying about objects that may never have been rendered or behind something else and so never need to be processed, you don't have to worry about it. To me, it's very much like a 2.5D image of the scene. You've already created this flat world, but you have additional information on each pixel that allows you to go through and do all of your lighting and shadow calculations way after you've processed your geometry, right? However, if you take a look at how this is processed, because it's throwing everything away early that's not visible, you don't have the ability to have transparency. You don't have the ability to have things layered on top of each other because you're dealing with a final static pane, an image, right? With all the detail right there. You would potentially need multiples of these, right? To have additional objects that have transparency behind them. And this is also reflected in how it uses the data structure. If we take a look over here, right? Notice here that alpha is 2 bits. Here, alpha is 2 bits in these particular cases. There's nowhere that we would even be able to fit this transparency information. There's an on and off, and that's pretty much it. So we couldn't do anything with it even if we wanted to. And look at the size of the G buffer. This is another big constraint, especially on mobile gaming. The G buffer is at its smallest 160 bits per pixel, right? As opposed to 32 bits per pixel with the forward rendering pass. So that's pretty bad. And if you use HDR, high definition rendering, that's 192 bits. And then if you look on their website, it can exceed over 200 bits per pixel. You need a pretty massive, well, not one buffer, but multiple buffers to store all that data, which is why it's not always used on all hardware. So mainly what it comes down to here is that the complexity now is not determined by iterating over each light and having these loops for every single object. Instead, everything gets processed, right? And every additional light you add does not cause an n increase in each object's calculations. All the objects are already calculated. For every light you add, it's only going to influence the pixels that are now on the screen, right? So you have a max cap of how much you can process, which makes it much better. So here, especially with smaller lights will influence fewer pixels. Fewer pixels being influenced means fewer calculations by your fragment shader, which means faster processing overall. So you can have those 100 lights that I was talking about before, and I used the example of a candle specifically because they're small, and the processing won't go up immeasurably high. Now, if you had all of those candles be stupidly bright in your scene, right, and influencing all the pixels on the screen everywhere, then yeah, you're really wasting what the G buffer deferred rendering is all about in that case. Now, once again, if an object is transparent, you don't get an option of using deferred. It's going to default to the forward rendering pipeline because it simply cannot support it with deferred. With deferred, you've got a flat image. With forward rendering, since each object gets processed one after the other, and then it's output like, oh, here's the pixel value for this location. Oh, you don't want to use it? Fine, throw it away. You do want to use it? Okay, keep it there. That's the issue. That's the difference. Another thing here is that each game object is rendered once, and the values are recorded then into the G buffer, all right? But then there's a separate pass specifically for lighting, and that's where instead of processing the entire object again, we just look at the G buffer. So, right, you process everything in your scene, then when you're done with that, then you process the light separately. It's not a lighting loop within processing of each object. They are separated from one another, which is why the G buffer excels at lighting calculations. If you want to look at some other information that's way beyond the scope of this class, I put a link right here to Unity's website, which talks a little bit more about how the G buffer works with the standard lighting model and so forth. Let's see, do I want to say anything else? No. All right, so now that you have an idea about those two rendering pipelines, we can talk a little bit more about the standard shader, PBR or PBS. So if you would like to learn about PBS's implementation, unfortunately, I contacted Unity about it because their links are dead on a few of these. I believe the Disney model, which is what they call it, it's just a different model that's being used. That's used for diffuse. Specular uses something called GGX, Visibility term is another version of GGX, and then the Fresnel approximation is a Schlick-Fresnel approximation. I don't expect you to memorize any of these. This is just if you want to go that this is where you enjoy the material of the class and you don't care about a grade and you want to do some on your own time learning. That's what this is for. You can go and check those models out because this is what's being currently used. As I mentioned before, energy conservation, energy out must never exceed energy in. Therefore, things like the specular highlight are important now. Before, the specular highlight was separate from the diffuse term, right? Each one was calculated independent of the rest. But because the total energy has to be conserved, when an object becomes more specular, and remember what that means, you need to have a fundamental intuition about what diffuse means, what specular means. Specular, you remember to those images, right? We had a picture of a surface, and we had a light coming in, striking the surface, right? And then it came off. And if it goes off in all directions, that was the diffuse. That's in all directions. That's the flat color of the surface, right? It doesn't matter how you view it. But with specular, it strikes the surface and goes off in a very, well, usually tight cone. Now remember that exponent that you raise it to determines how wide that fall off is of that specular highlight. So if it's a low exponent, it doesn't get raised to a very high power, so it's very wide. However, if it's a high power that you raise it to, right, you're now making that quickly accelerate very fast. That's what exponents do, right? And what happens is you get a very narrow cone of vectors shooting off in one direction, okay? When the light strikes that surface, right, it's going to contribute to both diffuse and specular. However, if it's mainly specular, if it's a very smooth surface, that means all the light rays hitting this object are going to be going off in that direction. Therefore, there are now fewer light rays going off for the diffuse term. Therefore, a highly specular object is going to appear dimmer than the diffuse one, okay? And by dimmer, I mean overall. It's still going to have that highlight on the surface, right? That bright spot, but the rest of the surface will appear much dimmer when compared to a surface that is very diffuse, that is not shiny, that is very rough. And I use the term rough because that's actually one of the terms we discuss. We talk about smoothness and roughness of objects in the PBS pipeline. So the smoother the surface, the stronger and smaller that highlight is going to be. So try to get an intuition, right? Because that's the kind of stuff that's going to throw you up on an exam. The questions I usually ask, if you know the answer, I mean, obviously, they're not going to be calculation intensive, right? I will usually make it to where if you know what you're talking about, if you read the notes and you know that the dot product of a vector pointing in the same direction as another vector is going to be 1, you don't have to sit down and do the calculation. You know it instantly. It'll just happen. So typically in my questions, if you have this kind of information, you can double check yourself, right? Oh, well, George didn't say, the literature says, and George reiterated that diffuse and smoothness, or that specular term, are opposites on a seesaw, right? So if I got a lot of one, I can't have much of the other. So you should be able to tell that when your values are not correct. Next up, we need to talk about high dynamic range. It's not on by default. It is something you enable. However, it's really important, and you've seen it in a lot. I know Skyrim really popularized it with, I think, that opening scene where everything kind of gets blown out on that cart ride that seems to be ported to every system out there. But the idea is that normally you deal with either integer values. Once again, huge mistake when everyone was writing their shaders. Everyone was using integer values when those were floats, so don't do that. But more importantly is, if you're dealing with ints, it's 0 to 255, or 0 to 255 converted over to a 0 to 1 range using floating point values. So 255 divided by the maximum value, which is 256 values, is what you're dealing with for that. So normally that's stored as an 8-bit integer. And the idea behind that value is it's the minimum, the lowest possible, pure black that your monitor, your display can output. And then it is 1, or 255, the maximum intensity that color can output on your monitor. It's mapping to your monitor. And usually there's a function as well for CRTs or different kinds of monitors that will then map it to its particular color space. Or you'll have a color space installed on Windows that will modify that as well as the output. What HDR allows you to do is to choose, is to use floating point numbers beyond 0 to 1. I believe, for some reason I have in my head -9 to +9. I might be wrong on that one, but I think that's what I've seen. And the idea is you choose the start and end of that range. If the range is the entire thing, obviously you're going to have huge missing segments because you're trying to squeeze a spectrum of values into a monitor that doesn't have the precision to show them. Instead, though, if you choose a range, right, if you pick a range within that, so when you're inside, you choose a low range, maybe like -2 to positive 0.5 or something, right? And then you walk outside, you can adaptively change that range as you move into a world. So what would you do? How would you figure that out, right? You just take an average of the pixels on the screen, right? You just sum them up. And what is the value that you get? If that value is above the range you're dealing with, then you could adaptively just move that little range up until the median value falls into the median of your range, right? And now you can see the highs and the lows when you walk outside into a sunny world from your candle cultist room instead. So that's HDR and why we have it and why it's a very popular thing and why it reacts it's replicating the natural vision you have as a human being, right? So you walk from one room to the next, and what happens? Your pupil dilates based upon the lighting intensity. It's doing the same thing here. All right, a little bit more about HDR. Actually, I think I kind of covered most of this already. In Unity, HDR rendering is performed to an HDR buffer. That's an important thing to understand. The buffer is going to change because it does need to have additional data. If you think about it, at the end of processing, if you're doing HDR, you don't calculate HDR at one step and then convert it back into the range, and then calculate it again and convert it back to the lower range and do it again. You do HDR with everything. So all the color values that you're processing need that full precision of a floating point number, right? So that means your buffers, your variables, everything is going to get bigger until the end, where you would then map it to whatever range you're working with, whatever range your scene calls for, and what, of course, the monitor supports. This is very similar if you're even lightly into photography and you happen to ever own, a real camera as opposed to a cell phone camera, like a DSLR, or some of the new ones don't even have lenses anymore. But the idea is you can typically shoot in RAW mode. Many people, for some reason, don't know this. It's an option. Everyone shoots in JPEG and they get compression artifacts because it compresses the image down, so you get, an extra couple thousand photos, but memory is so cheap these days, who cares? With RAW mode, at least the camera I have, it's 16 bits per pixel instead of 8. And what that allows me to do is if I botch a shot, which happens a lot, I can go back in and I can adjust the range of the shot. It's not going to save everything. If it's blown out completely, that's what it is. Actually, you know what? I think 16 is incorrect. I think it's 12 bits for some reason off the top of my head. But either way, it gives me some grace, right? It allows me to go back, and if the shot was a little bit too dark, well, it captured some values that are darker than what I can see. And if it was too bright, well, I can pull out some of the values that look like they're blown out, but really it's got the data there. And that's one reason why, if you're doing any kind of photography, a lot of times doing it in RAW will save you if you mess stuff up, because there's only so much you can do once the data exceeds the ranges that it can capture. HDR is something you need to enable. So if you go to your camera inside of your inspector, here's your camera over here, you will then come on down and you'll see right here is HDR. You can use the graphics settings, or you can, of course, override them to be whatever you want to. And the most important thing to understand is that an HDR scene always has to be what's called tone mapped back to a range that's displayable on your monitor. If you don't do that, you're going to get a very narrow band, right? If your values are from -9 to +9 and all your monitor can represent is 0 to 1, imagine how much is missing. How much darkness is just pure black, and how much lightness is pure white, because your monitor can't support it. This is typically done through something called the post-processing stack, which is a plugin that's offered inside of Unity. Luckily for you, it's actually part of Unity. A few years ago, you had to download it from GitHub, and it was a giant pain in the rear to get set up. But these days, it's all built in. HDR only works for forward rendering. So that's another thing you need to understand and be careful of. Once again, you got to make choices between which ones you want to work with. Actually, hold on a second. Let's see. HDR. Oh, I'm sorry. It only works for forward rendering if the post-processing effect is on the camera. Deferred rendering, because I knew this was wrong, because the deferred rendering bit size is greater because it supports HDR natively. So Forward rendering, you have to put a post-processing stack on your camera for it to work. And when we get to actual implementation, which is going to be a little bit later in this course, actually not much later, maybe after the midterm is where we're really going to get to making stuff. I will explain the post-processing stack and how you can implement it because it really adds so many features to your virtual world. Okay, so we discussed lighting and all that great stuff, but now we need to talk about the materials, right? Because lighting is half the equation. The other half is when the light strikes an object, what happens? And for that, we need to talk about the standard material. As you were creating objects in the beginning of this course, until you started making your own shaders, you were probably given the standard material as the default one to work with. So when you create a new material, it's of type, it's a type standard. This is built into Unity 2019.4.x. It will still be around for a bit, so don't worry about that, as I mentioned before. But there are 4 subtypes that you need to be aware of. The first is, and this is what screws everyone up, so be careful here. When you select this, it does not support transparency by default. It will be set to opaque. This means it is going to render everything in a scene with no transparency. It does not matter if you set a transparency value. It does not matter if you pass a texture to it with transparency. It is flat out ignored. So don't, if it's not working, check that first. Next up, each of these is kind of, it's not quite in the level of expense, but that's a way of looking at it. So opaque is not very expensive at all. It's just the standard way we render things. Cutout is per pixel on and off. So it's a binary value, 1 or 0, right? 0 meaning it doesn't render that 1 meaning it will render that piece of it. It doesn't, because it's binary on and off, it doesn't require blending. So cutouts are actually really great for vegetation or any of the kind of things you see in many games. I mean, World of Warcraft has it everywhere. They use planes, right, for their trees and their vegetation and so forth. And if you zoom really far in, what's interesting is it's not a bunch of pixels like this. You would think with cutout, the pixels would get, it'd be jaggy. However, with things like mipmaps and blurring and blending and filtering, instead of being a stair-step jaggy pixel on a leaf, it ends up being this sort of soft fade off from place to place. It depends upon what algorithms you're using. But either way, cutout is very cheap because it doesn't blend things together. It's either on or off, so it's usually rendered after opaque, but it doesn't have to be ordered. It doesn't have to be from front to back or something like that. Now, fading and transparent seem like they do the same thing. But what you need to understand is that a transparent object is an object that is somewhat see-through. It's like a glass. And even though a glass is see-through, when you take a light to it and you have it at a grazing angle, you get a shiny specular highlight off that surface, right? It doesn't matter how transparent that glass is, the light is hitting it, scattering off, right? And reflecting off, and it's creating a highlight. If you want those sorts of effects, that's when you use transparent. However, if you're making a game in the future and you need to make a teleporter that teleports an object from location A to B and you want the object to fade out, including all of the lighting on that object, everything about it, you would then use fade instead. So fade is about an object, becoming a ghost or an apparition. Everything about it is fading out, is going away. The lighting, everything. Transparent is where you're trying to be closer to reality, where even a truly transparent object is going to have light bouncing off of it because it's changing from one medium to another. And whenever light moves from one medium to another medium, light will naturally bounce off the surface. Doesn't matter what it is. Okay, so do understand the difference there and when to use them. Fade is really good for UIs or items fading in, like health ones or respawning stuff. Transparent is good for real world effects where you need something that looks transparent, like glass and so forth. Okay, so a little bit more, of course, is physically based rendering. It's used everywhere. It's used in Unreal. It's used all over the place in most engines. I haven't seen, Timber something from Amazon. I haven't played with that. Actually, if you care, I do a little bit just because my kids play it all the time, but PBR is coming to Roblox, which is a horrible looking game that uses ambient diffuse and specular stuff mainly for everything. But they are to a limited number of people, not me, unfortunately. I got on that train too late, but they are opening it up. And you can actually right now in Roblox Studio, import in PBR materials and get everything ready so that when they do the switch, you'll be able to swap out all your materials from the old pipeline to the new PBR pipeline and have things that look much closer to Unity, of course, and what it looks like standard. And don't diss Unity. I know I did it. I know I did it a long time ago. But people look at the Unreal Engine and then they look at Unity and they're like, why doesn't Unity look as good as Unreal? What's wrong with Unity? And the reality is, Unity doesn't have everything turned on. Unreal turns everything on. So when you open that engine up, it looks amazing. And you're like, wow, this is incredible, right? Unity, though, doesn't do that. You need to know what you're doing to turn on the extra stuff, the post-processing stacks, the volumetrics and so forth, the lighting things, right? It's two different ways of looking at the same problem. Unity also is used all over. I don't know how many Unity games I've downloaded from Steam, where like $1.99 games where people haven't even paid Unity to use the engine. They just use the free version because you get the splash screen that pops up. It's used all over the place and it's simple and easy to work with, and it supports a ton of devices. It's easier to add than it is subtract. And that's true of anything in life. And when we get to 3D modeling, you will really see that, where if you start with an object with 1,000,000 polys, good luck getting that down to 5,000. Whereas if you start with 10 polys, it's very easy to get that to look good up to 5,000. Anyway, tangent. Anyway, so object, diffusion, pops off, or reflection. So that's once again diffuse and a specular term. We're still not away from that ADS stuff, okay? Here I say instead of calculating ADS, we're still calculating ADS, but with a limitation, and that's the energy conservation one. And here is a really good image. This link came from the Unity website, which came to this other website here, where they show a diffuse surface, which looks brighter, right? But then they show the same specular or very shiny smooth one. Now, one part of it is dimmer, but at the same time, it's also reflecting the environment around it, and the environment around it looks dimmer as well. So do understand that that's tainting this a little bit in this particular case, but overall, it's going to become dimmer because of it. Metals are another thing. Really, if you've done anything with graphics at all, even just playing around with your friends, making some sketches or whatnot in Photoshop or any similar program, to define the metalness of an object is not something anyone has intuition with. And it takes a lot of time to get used to it and to just use it and accept that this is a property that light interacts with, and it should be part of the object. So here we have that portal-esque cake I made a while back ago, and these are different objects. This is the one before. This is it with a flesh, really highly scaled flesh. I think it's actually the elbow skin of a middle-aged female is what the material is actually described. And yes, they do get that specific. But over here, we have the metal versions of it. And what's interesting is the specular highlight. And specular highlights with metals. Metals, the electrons will actually interact. I don't know the physics exactly behind it. That's not my area of expertise. However, metals typically will cause the specular highlight to get a tint of color similar to whatever the color of the surface is. And that's a huge difference between non-metals and metals, is how the specular property is dealt with. And that has to do with conduction, and that's why we call them metals and non-metals. Conductive or metals objects have high reflectance usually, and they usually tint the object. However, non-conductors or insulators like skin and so forth, or the grain of whatever this is that I put on this cake, don't do that. And so they don't they will absorb the light, they do not scatter it back out, and they will not have that property. So what's interesting is you get a whole range of metal between 0 and 1, and really you don't use the whole range. You typically have objects that are somewhat metallic and somewhat not. Usually the metals are on one side and the non-metals are on the other, and you don't mix and match them too much. Next up is the roughness term, or the inverse, which is called smoothness, which of course is just 1 minus roughness. And do understand that in some places you will hear it called roughness, and in other places you will hear it called smoothness. Just understand that they're opposites of one another, and it's just how the pipeline does things. Roughness, of course, comes from those microsurface details. The light bounces off the surface, and it goes in different directions, and it becomes diffuse. The higher that diffusion, the less reflectance. Once again, going back to the similar specular type stuff. This is usually called roughness or a glossiness value. And I will say, don't be too overwhelmed with the terminology. Even people in the industry get them wrong and use them inappropriately. And you just need to be careful. That's all. When you're actively developing something or working in a pipeline, understand what it is you're trying to do more than what the name is. Because names, there are so many instances that I could talk about people naming things incorrectly and having huge repercussions on the industry. Heck, you're all ECEs. Polarity, right, of positive and negative on electricity. How wrong were they on that one, and how has that influenced everything after it? Same thing happens in computer graphics. So just be aware of what you're trying to do. So the higher the roughness, the more light is spread all over, right? It's diffused out. And the fewer photons, not photos, photons, that enter the camera in that case. So it's going to appear dimmer. The rougher the surface, unless it's a shine, if it's going straight into the camera, then you have all the photons directly going into that area, okay? The Fresnel effect, and yes, once again, French, so get rid of that S. It defies English pronunciation. You will have to YouTube that and listen to some robot tell you how to properly pronunciate it. But anyway, reflectivity varies based upon the viewing angle. Now, this is an interesting characteristic of matter, and you can see it here in this photo I took from scratchapixel.com. Here you have water, right? And here, off in the distance, as that angle gets further and further out there, as it's a grazing angle, it's highly reflective, right? But then when you're right over top of it, you can look straight down, perpendicular to the surface, and you can see a fishy swimming, right? Because it's not highly reflective. So do understand that that angle influences how reflective an object is. And that's the same for this image here of a table. Notice how it becomes highly reflective as we go from perpendicular to the surface down to the grazing angle, right? Almost parallel to it. You can see far more of the scene. And go ahead and give it a shot on your desk or whatever surface you are. One of the books I used to read challenged you to take a piece of loose leaf paper, flat, shiny, put it down, and try to get as low as possible and see how much you can see of the world, the reflection in it around you, even in a very diffuse object like a piece of paper. I never got it to work very well, but maybe you can, I don't know. So anyway, smooth objects can become very mirror-like at grazing angles. And more importantly is even if it's not smooth, at grazing angles, you're going to have a brighter intensity there because it's highly reflective. So even for diffuse objects, it should become brighter around grazing angles. So because of that information, if we were looking at a sphere, right, what's a grazing angle on a sphere? The entire perimeter of the object. And this is why in a lot of renderings these days, what you'll notice is you'll have, your light source up here and you'll have this bright light over here. But then what you also have is you'll have this tiny little kind of shine that goes around the edge, even sometimes to the backside of the thing where you don't think there's light. But that's it approximating the Fresnel effect in this case. With the Fresnel effect is also interesting because here you can see, very similar to what I was talking about here, this is the center of the object, perfectly perpendicular, 90 degrees, and here's the edge of it, and you can see that reflectivity becoming much stronger in this orb that's being used. And then there's also a reflectivity value. And what you need to understand is that not everything is controlled by you with these rendering pipelines. Some parts are internally handled because it's just too many variables to deal with to control things. And many times the edges, if you notice, while off-center, chrome and rubber have highly different reflectivity. When it comes to right on that edge, that part right around the silhouette, you'll notice that they converge. And this is what we care about in this particular case, and with producing the Fresnel effect. This can be handled by the smoothness of the surface and doing render probes and so forth to put enough of a reflection on it to make that object look correct. But this area here, specifically targeting only this part of the object around the edge, this is non-linear. That's why we have to implement the effect ourselves, and it doesn't work in the pipeline as we see it today. Unity has a series of charts. I'm not going to go deep into these. This is the kind of thing you can mull over in your own and think it's interesting or not interesting. But take a look. They have the the range of albedo, these are the colors that you work with and what range they fall in. And notice that for non-metals, it does not go all the way to dark, and it does not even go all the way to perfectly white, okay? And for metals, it will go all the way up there, but once again, it doesn't go way down here. So for metals, you're dealing with much brighter looking surfaces typically, and non-metals, you have a larger range, but never quite being as bright as a metal. And you can see that in these examples over here: gold, brass, copper, iron. Notice how bright all of these are, as opposed to coal, rubber, mud, grass, and so forth. All of them are much, much dimmer. And remember, this is the pure diffuse color. If light hit that object and went out in all directions equally, this is the color we would use to describe that effect. Then we have the metallic property over here. You'll notice it says R. That's because this is actually a grayscale property. It's stored in the red channel of the texture, though, in order to conserve space. Smoothness as well is a single scalar value, so they put it in one part of it. So rather than having multiple textures that are wasting channels, we can condense all of these into a single texture. And Unity's current pipeline doesn't do that. If we want to, when we get to the lesson on implementing your own effects, we can talk about the MAU's pipeline, or it ended up being changed later on to Mo's pipeline that I developed, which is metallic, ambient occlusion, emissive, and the specular or glossiness of it. And it's all contained within one texture, which is compacted, and it's far more efficient than spreading it out across multiple ones. Once again, you do have to worry about efficiency when you have scenes with gigabytes of textures and condensing things down into a smaller size. That's not even compression either. We're not even talking about that stuff yet. So then metallic, we have grayscale values. Low metallicity values are black values, and then high metallicity are the white values. And you can see the difference in the reflections of the surface as we move across it. Then, of course, we have smoothness, which is, yes, it's going to reflect light, but do you see what's within it? That is, do you see the environment around it? And of course, metals and non-metals have different properties. Metals, you will be able to actually see everything. Non-metals, yes, the specular highlight becomes tighter, but there's a lot of subsurface scattering going on. So you never actually get a picture perfect view of what you see with the metal. This is one of those things where sit down with it and just quiz yourself for a few seconds. Say, all right, you know what? I'm looking at a metal. What would I expect it to be if it had a high smoothness or a low smoothness? And just have a mental picture of what that might actually be. It will help you out. No, I'm probably not going to ask a question like draw the difference between a smoothness, low metal, and a high metal. But I could very well ask you, what are the properties of a PBR shader? Okay. And hopefully if we have a homework assignment and I've told you to use the standard shader and plug these values in, you would be like, oh yeah, I remember I needed that metal thing, I needed that smoothness thing, and there was that just the color of the surface. That's the kind of intuition I'm looking for in the theory that you understand. Okay, so how do I get this stupid thing to go away? I always hate this. Yes, we're going to move you to a different screen is what we're going to do. Thank you. Okay, so now we can get to the actual surface shader stuff. And the surface shader, as I mentioned before, it's a function. It's not a vertex function or fragment function. It runs on the GPU, but it's contained within a bunch of Unity code. So it's probably going to either be processed on the vertex or the pixel shader. You don't know where. Remember, depending upon what pipeline you pick, right, deferred or rendered, and depending upon how you set up the lights, some parts of it might be, in the vertex shader, some might be in the fragment shader. You don't know. It's an abstraction of an existing pipeline that makes things easier for you, hopefully. That's the idea, is that the standard shader, if you were looking at the vertex and the fragment shader, thinking to yourself, this is kind of tricky. There's a lot of stuff to deal with and handle. The standard shader is meant to, do some magic hand waving over that and say, look, all of that transformation stuff is gone. All of those semantic bindings are gone. Now you just deal with what happens at the surface and we'll handle the rest. What you're really doing is you are defining the surface color at that location. That particular pixel, you are saying the output for this are a few different things. Here it is. These are the properties of that particular pixel. Do with it what you will, engine. And then the engine will do its thing behind the scenes, or the other code, the rest of the code in the shader, the surface shader that you don't get to see unless you dive into it yourself. So of course, importantly, You do not need to transform the points. So gone is that Unity object to clip space function that you had to call where you really didn't know what was going on, but you knew it had some matrix multiplications. You don't need to worry about that now. You will be given that information and you can use it however you want to. Another thing too is that it does not give you complete control. And that's very important to understand. The surface function, you can't do everything with it. And that's where, when you're doing advanced effects, when you're doing really interesting stuff, you need to go back to the vertex and the fragment shader to make things actually work. You can, if you want to. We're not going to cover it in this class because it goes beyond what I expect of you. But you can have a vertex-esque shader, a vertex modifier that can modify the vertex data that goes into the surface function, okay? But once again, you're plugging into the larger Unity shader that's being operated here. And then there is an optional lighting model, which we'll talk about at the end of the lecture, where you can determine how you want lights to be calculated, especially if you don't want to use the physically based shading one. You don't want to deal with the constraints of having conservation of energy. And that matters when you're doing things like toon shaders or special effects. But the reason is, why wouldn't you just write it all from the ground up? Because maybe you're not good enough yet. Maybe you're just learning. You want to get your first game out there and have some fun. And the surface shader does the heavy lifting, and it allows enough configurability to where you can do things like add a toon shader to it and still rely on all of what Unity gives you to make it work. That's the importance here. Oh, also, Unity documentation on the nuts and bolts, like the real low-level stuff, is sparse at best, and you usually have to pay for it. You know, we're talking thousands of dollars in one of the higher-end tiers. So using the standard shader is a great way to save yourself some money in the long run. Next up, I want to take a minute and talk a little bit about tags with shaders, because this is going to start popping up when we deal with transparency. And understanding that the tag has some importance will help you out. One of the tags is called Q. And you can think of Q as a series of bins, out in front of you, and the bins furthest on the left get rendered first, and the ones furthest on the right get rendered last. Let's do it that way. Why not? You have a series of bins that are already predefined by Unity. Background, which is your skybox or maybe a flat color, that gets rendered before everything else. That's the value, an arbitrary value of 1,000. 1,000, 0 to 999, you could technically use for anything else, but 1,000 is where there's a cutoff. And then you have another 999 values until you get to geometry, which are opaque objects. And then there's alpha test, which is, the on and off, binary on and off. That's somewhere between geometry and transparent. And then you have overlay. The interesting thing about the Q is you can create your own bins. All you have to do is you can either use an existing keyword like geometry and add an arbitrary amount that you want to it, and this will put a new bin in between it, and any geometry that uses this shader will be rendered in that order. So background geometry, and then your stuff will be rendered. Usually, it's not as cut and dry as that, is what I'm going to say. One of the biggest reasons to have, one of the biggest reasons you want to order things is to have control as to what shows up on the screen. And usually you want to do things that breaks standard convention. Like you want you're making a Five Nights at Freddy's game and you have a giant texture of an evil rabbit, right? That's trying to kill you. And you want that to show up in front of everything, regardless of what's being rendered or what's on the screen. In which case, you would want something like the overlay layer, which is on top of everything else. But what you also need to understand are some of the subtleties. This is when it gets rendered. However, I mentioned before, there's things like the depth buffer, which is a buffer that holds depth information of the closest pixel that has been evaluated. So if you have a sphere that's far away, the depth buffer is going to write that sphere with grayscale values, and they're usually floating point values between some range of like 0 to 1 or something like that. It depends. But that value will be rendered there on that object. And then if you render another circle, which is further behind this one, so it's the same place, but further behind it, when it's processing these pixels, it's going to look at the depth buffer and it's going to reject them because it's behind it. It sees the depth values of this object, sees the depth values already recorded, and it will throw away ones that are behind it. However, if a star shows up right in front of all of these and it gets rendered later, say you put it in the overlay one, it will then cover everything, okay? However, if we did the same thing again, where we put something in the overlay layer, like a rectangle, right? But it's behind everything, but we think I put it in the overlay layer. That's going to be rendered last. It has to be rendered on top of everything. You're forgetting the fact that there's a depth test performed. And even though it's rendered last, unless you disable that depth test, all this stuff here still shows up on top of this object here. So once again, understand the bins are there to tell when something, my chair is really noisy. It's there to put things in bins, but you have to have a sense of what's really going on behind the scenes. Otherwise, you will go crazy, not understanding why objects are not rendering in the order you think they should. Okay? And that's what this class is all about, is really giving you a good look behind the scenes as well, so you don't make these mistakes that forums are filled of people asking why this doesn't work. So as I mentioned, 5 queues, integer values, lower ones render first, higher ones render later. You can make your own if you want to. Another thing too is remember that they're key value pairs. This is very different from anything else, and it's part of what I hate about writing shaders in Unity is it's like different languages, right? You got the C stuff, then you got this kind of pseudo meta stuff with the tags and whatnot, using brackets here, but then brackets aren't used somewhere else, and it's kind of a mess. Just try to burn that into your brain. It'll make debugging a lot easier. It's double quotes, right? A name equals, and then double quotes, and there's no commas, no semicolons, no nothing between additional tags. It's all quotes equals quotes, and then quotes something equals quotes, something else. That's all it is for each tag. There are a few other tags, just throwing them out there so that you have a sense of what's possible. Render type. Is it an opaque object or is it alpha tested? Once again, this is another spot where people mess up. They think, oh, I put my object in the transparent bin, but it's not transparent. All you did was specify when it should be rendered. You did not specify anything about how the transparency or alpha values should be handled, okay? That's a big mistake that people make. Disable batching. This is an interesting one. It might not make a lot of sense to you right now, but it's the kind of thing that if you spend a year doing stuff and you go out there and do some interesting work, this could bite you big time. What it means is that all the geometry is transformed automatically into world space. You do not get a reference to object space. And because of that, you're locked out. You might be doing calculations that require knowing that world space or require you moving from object space back to world space, right? You might have to do unnecessary matrix transformations to try to get yourself back there if necessary. So this is something that you'll see, you can turn on or off. It's an esoteric topic. It's out there, but just know it's there. Force no shadow casting. This is a really important one for transparency because usually transparent objects, you don't want shadows cast because they're see-through. So you need to turn off certain features. Ignore projector. This is one that I spent over a day investigating. Don't worry about it. The projector is a component you can add to objects, and it will project a material. Unfortunately, there are no built-in materials that work with the projector object. You actually have to download the standard asset pack from Unity's store to get shaders that work with a projector. So you're never going to run into it unless you specifically want that feature. So you can pretty much throw that one out of your brain. Sprite atlases, we're not covering two-dimensional games, but an atlas is typically an image with lots and lots and lots and lots and lots and lots of sprites. Think about the old NES games, right? You'd have a sprite sheet of all the different animations that a Final Fantasy character would do. A mage would have a walking, the different animations and so forth. And you step through the sprite sheet, and each one would define a different set of animations. Don't worry about this stuff. You're not going to come into it anytime soon, probably, unless you're specifically targeting 2D type stuff. Preview type. This is an interesting one. That's the inspector. So if you notice at the bottom of the window, you have the preview type. Well, normally it's a circle or a sphere. You can choose different objects because sometimes it doesn't make sense to use a sphere if your shader is meant to just work on flat terrains like a plane or something. Now, this is an important one. It's for those of you who end up taking this a step further and want to know how things work. You have free reign of diving into the Unity shaders and understanding how they work. all you have to do is find where you installed Unity, go into editor data and the CG includes file, and literally open up all of the CG includes. Right click open with Notepad++ or whatever you want to, and it's all the CG code right there for you to work with. Many times, shader stuff is not documented, or if it is, it's wrongly or improperly documented. And frequently, when I run into those problems, first place I run to is just going right in here and start just looking for the code, looking for exactly what I want. And it does make sense. There's a logic to it. Notice there's a lighting one, that's general lighting. And within lighting, there's actually other ones like common lighting utilities, Unity CG, CG specific stuff that Unity incorporates, G buffer, like what we talked about just a second ago, tessellation, which we'll see how the semester goes on the midterm. I really want to talk about creating your own tessellation shaders, which allows you to drastically increase the detail. The idea being if this is your surface right here and this is one polygon, you subdivide that into multiple polygons and then you perturb it so that you can get all kinds of crazy bumps and ridges and so forth that are far beyond the capabilities of you pushing into it from the data from the application side into the GPU. That's kind of the idea, is you generate detail on the fly to make objects much more interesting and, more importantly, take up a lot less space than they normally would. So I encourage you, if this stuff is at all interesting to you, this side of the thing, this is where you want to go to check stuff out. And if this stuff doesn't interest you and you really took this class for the 3D modeling and the getting this stuff done, don't worry. After the midterm, that's where this class is headed. So you're going to be doing a lot of good hands-on work kind of stuff. So gone are the semantics, which I'm sure all of you are so sad to see go, right? So no more are you binding to SV position anymore, right? Because you are using Unity's stuff instead. So for that, you have two structs that are already defined for you. And the reason there's two is because the PBR or PBS pipeline actually has two somewhat parallel pipelines. They're almost the same, but there are subtle differences. The surface output standard pipeline, as it's called, the reason why it has this long, nasty name is because, unfortunately, in 5.x and before, Unity implemented a surface output struct, and that name was taken. And in order to keep backwards compatibility with everyone who did it, they had to append to that the new model, which is called standard. So that's why it's surface output and then standard. You will find just a surface output model, and actually we see that at the end of this class today. But just be aware that this is a two-parter, okay? Then there's surface output standard, and then there's an extra little bit on the end. Yes, it's the standard pipeline. However, we want to have specific control over the specular component. That is very important. Up here, you don't get control of the specular component. It is derived from the color you choose. Remember that image where I showed you the pictures of gold and silver and all the other ones, right? That color is going to be used in a specular calculation. If you wanted precise control over that specular color, the surface output standard specular pipeline gives you that control by having a specular term. Notice the differences. Albedo up here, that's the flat color surface. Specular next, normal here. Emission, smoothness, occlusion, alpha. All right. We will only be using this pipeline up here because, quite frankly, I think you have enough stuff to learn without having to throw specular control on top of it. But do be aware that it's there, and if you need specific control of the specular highlights, so be it. Why do you really need that? Why do you need anything in life, right? Because someone's going to come up with a cool reason to have it. Maybe you have a cool force field effect, right? And you need to control the specular highlights color to be a crazy different color than the rest of it to indicate how, not light, but maybe you're using the lighting calculations in this whole thing to instead do some sort of a crazy laser vision thing. I mean, you can come up with any reason you want to why you need that control. And that's why it's there, for crazy people to come up with the crazy cool ideas and do interesting things. So like I mentioned very briefly, the old surface shader exists. Just be careful. This is going to be a reason you get errors in your shader. I'm going to tell you right now, you're probably going to go online. Maybe you'll copy a couple lines of code, and then you'll get this error like not expecting surface output, expected a texture 2D or sampler 2D or something else instead of this particular thing. And it's because you're using the wrong one for the pipeline you're working with. I'm going to say it one last time. because I know it's going to hit someone. Beware of surface output and surface output standard and surface output standard specular. They are different and they will cause you errors. Please write that down. Okay? Anyway, you saw the structs up here and what they contain. Notice here we have a similar struct, but it's different. It's legacy. Albedo, color, normal, emission, specular, gloss, and alpha. And these two terms are actually condensed in the other pipeline. This is much more similar to the ambient diffuse specular pipeline from before. Okay? With the normal and the light in the scene, you can do diffuse. With the specular value, which is a 0 between 0 and 1, and then that gloss value, you can calculate the specular highlight of that scene. And then, of course, the alpha will tell you whether or not it's transparent. So while we can't bind semantically anymore, we still need to inform Unity what data we want into our function. Okay, you could pass everything, but that's not efficient. So instead, we specify with our own struct from a collection of variables Unity gives us. And that collection is down here. Don't memorize them. I don't ever ask questions like that unless it needs to be something like this, just brutally, simple or basic. I hate brute memorization because these days we just look stuff up. Or when you're really doing something in the field, it's important for being a doctor, right? But when you're coding, you can look this up. You have docs for this stuff. So you have things like the UV coordinate. Now what's important is, let's see this in another slide, is this is actually just UV underscore. And this part over here is dependent upon what you name your textures. Be aware of that, all right? That's an easy thing to mess up. Also, UV underscore 2. As we saw before, you can have multiple texture coordinates. In Unity, this is their system for doing that. And I'm going to use the templates or generics in C# method of defining the optional part, or where you placeholders, or Mad Libs, what you put in here, the underlined part. This is the name of the texture, this part right here, okay? And then we have, we have the UV coordinates and however many coordinates you support. We have the view direction, where you look. So that's the camera's view direction in world space, if I remember correctly. We have a color if you have one. The position of the screen, where that is on the position of the actual screen, which is an interesting one if you need to do screen space effects, which means it's not about moving through the three-dimensional world, but where it happens to be on the screen itself. World position, that's an important one. You'll be using that a lot, where it is within the entire world. And you'll notice what's happened here is Unity's transformed most of this stuff for you into a convenient space, world space, for you to work with. You can move things back and forth. There are matrices, if you look them up in the docs, that will allow you to multiply by them and move them back to other spaces if you need to for some reason. But usually a lot of these calculations can be performed in world space or around world space. And then a few of these other ones. The only thing I want to mention to you is notice that there are these caveats. If you look in the documentation, if nothing is written to the normal vector, then you have this value. If nothing is written to this other thing, then you have this value. Or if you do write to the output normal, you need to specify this little doodad over here, internal data. So if you're doing more complicated effects, to fit everything in and to make sure you're getting the right data in the right slot, you might need to add this internal data on the end. Just file it away. George said something about, world space reflections normals. Things aren't working right. He said something about needing maybe some sort of a keyword on the end that signals the right thing. That's all you need, is just leave it back there. You can look it up in the documentation later. So you're going to define your own struct, but you don't do any of the semantic bindings because that's all taken care of. You're within Unity now, okay? Semantics are handled by it. The talking to the hardware, that's all handled by Unity. You just care about selecting which variables you want. And importantly is you must have one. You cannot have an empty struct. You have to have some input for this to be processed. Typically what you'll see is most of the time that's one of the UV coordinates, like UV underscore main text. By default, I believe, is the one added when you create a new surface shader. And I already mentioned the textures and the samplers and the naming convention. Here, if I had a texture property called underscore main text, of course it's UV underscore main text. If I had a decal, which is a different kind of texture, we can do a UV underscore. It doesn't matter what kind it is. I just wanted to come up with different options for you. Whatever you call it. Here I do height gradient text instead. and I want to sample a different UV set. So I make sure it's whatever UV set I want. And of course, that height gradient texture value as well. Then of course here, I'm just adding a few more. This is just so you have something for reference. Just like before, we use the vertex and the fragment shader and the pound pragma vertex, or the hashtag pragma, if you're your generation, I guess, fragment to inform the compiler how to connect our code together. The standard shader is still going to require a pragma, a preprocessor directive, right? But it's going to look a little bit different. Instead of just specifying vertex, in name here, or fragment and the name of your function here, we've got a series of steps because it does allow you to do a few things. First, of course, is, hey, I'm working with a surface shader. Okay, so it's the same thing as, pragma vertex or pragma fragment. Here's pragma surface. First up is the name of the function. So you would have a function called surf, right, somewhere with parameters later in your code, same as you did with vertex and fragments. But here is where things get a little bit different. This capital S is the lighting model, and that's the built-in lighting model that Unity uses. What you need to understand is that Unity is going to process your surface based upon what you provided, and you're going to put data out, data in, data out. And then optionally, there is it's not optional, you need a lighting model, but by default, it's going to be the standard model. So this data goes out, and for every light in your scene, this standard lighting model is going to be run on that light. And depending upon what code's in there, it figures out how to draw that onto the surface, all right? You can implement your own lighting model here and insert that function name there if you want to. Then you have room for optional parameters. Here, it's just telling it, yes, I want full forward pass rendering shadows. Once again, a reason why we took the time to discuss the difference between diffuse and, deferred and forward rendering is so that these keywords make more sense to you. When you see forward, you know it's using a forward rendering algorithm to calculate those shadows. So you need to define a surface function to begin with. And it's very easy to do. In fact, Unity is going to set up almost everything for you. And it's important for you to make sure, of course, that you're using the right version of it. Here, we're going to be using surface output standard in this class unless otherwise specified. And we'll do one example of an otherwise scenario at the end. But anyway, let's exit out of PowerPoint. Discard the annotations. That's not important. And let's see, where were we? We were somewhere around here, right? Let's jump into Unity. And once again, this is where, if you want to kind of follow along and you're able to, go ahead and create a new project. So what time is it? 6:31. So we're doing great. And let's just create a new project on the desktop. That's fine. Let's just call this standard shaders. Call it whatever you want to. Just don't call it I hate this class or something like that. And then a day from now, ask me to Skype in or whatever and see your code, and I see that as the project. That's always, demoralizing a little bit, especially when you read the code where those are the variable names. So if any of you ever go for your master's or you go become a teacher in some way, that's the kind of stuff that really hits you at the end of the day when you're at home grading papers. So let's see. Of course, Unity takes some time, so why don't we go ahead and keep talking. So when Unity loads up, it's easy. It's one of the options. We're going to right-click, create a new shader. We're going to choose the standard shader, surface shader. It's going to produce most of this boilerplate for us automatically, the pragma definition and so forth, and the bare minimum values that you're going to need. It's even going to put a surface texture, and it's going to process the main texture, the metallic, and the glossiness for you as well. So you will have a working shader without any effort whatsoever. But that's not the reason you're making a surface shader. You want to change something. You want to make it more interesting, and then we'll get to that shortly. So come on, Unity, are you here? Yes, you are. Okay, so I updated to 2019. Oh, this is 2019.4.6. I also added .12, and there are a couple differences with .12. We'll stick with this one for now. For some reason, the other one's dark mode, but this one's not. So let's create our new stuff. Once again, right-click, go to Create. Let's do a folder, and let's just call this Shader Examples. I'm not going to be clean. I'm going to just put everything in the one area. Of course, you should properly organize things for your project because you'll have more time. Let's make a new surface shader, and let's just call this Example Shader. And we'll also need a material, so right-click, Create, and let's go to Material. And let's just call this Example Material as well. If you wonder why my background's completely black, that's because I have things like the lighting turned off. Many times this gray to blue background is distracting, and rather than going and changing settings in the rendering or the camera, it's just more convenient to nuke it right there by disabling that, as you see. It's also great when you need to take screenshots. You need a flat background of a certain color to extract opacity or transparency information. So here we have example material and we have example shader. Now we need to, of course, hook this up. So let's go to shader standard custom and choose our example shader. Let's go to game object. Let's create a 3D object. And why don't we go ahead and create a capsule, everyone's favorite shape. And we will move this off to the side. And let's grab our example material and drag and drop it onto this object. And you'll notice for a second there, it flashed like something was going to happen and then nothing did. And that's because it's the generic basic shader. You're not going to get anything more out of this. In fact, it's actually cutting down on a few of the features with this shader. But for the most part, it's going to look exactly the same. Once again, let's go ahead and double click on the example shader, open it up in Visual Studio, and get that open so we can start editing things and making something interesting. So let's take a look here, get a sense of what's going on. It's the usual. We got our properties at the top. We got a few more than we're used to, right? We got a glossiness and a metallic, and then we have our main texture and a color value so we can augment the main text value. So we're starting to see how things are done a little bit more clearly here. And if you really take a moment to understand what's going on with each of these different variables and what they're providing, you start to understand how everything works and the capabilities you have. Next up, subshader, we got our tags. We talked about tags and importance of them. We have this set to opaque right now. Therefore, we should not be rendering with transparency information because this is rendering at the wrong time for that. Then we have level of detail. Don't worry about that. That's something we may talk about later, but it's not really critical for this class. Then we have the pragma. That's the most important one. Pragma surface. So we're dealing with a surface shader. Surf. And if we scroll down, we'll find a function called surf. Therefore, I mean, you could change this to be any name, and you are encouraged to give this a name that actually has something to do with what you're doing. So I'm just going to call this example surf so that it makes more sense because at the end of this lecture, I have a couple slides where I tell you how you can take all the code that you've written and put it into your own CG include file so that you can use it in all of your own projects in the future. That way you can reuse all the work you've done. And if you have 20 functions all called surf, it doesn't do you any good. So you might as well start giving them individual names based upon what you're working with. Then we have the lighting model, which is the standard one. And then finally, we do allow for full forward shadows. So these objects will have shadows on them. Next up, we talked loosely about the Pragma Target 3.0. This is the shader model being targeted. This is an old enough model to support most things. It's not going to support some things like the geometry shader, which is 4.0, and some of the later features, but it's great because it'll work on a large number of pieces of hardware. Of course, our sampler. Here's the other big difference. Here's our struct called input. And here we get to define what variables go in. As I mentioned before, by default, we only get one input value, and that is the UV coordinates for the main texture, which is up here. If this wasn't called main text, if we called this something else, like let's just call this example text, right? Horrible name, but we'll use it. Come down here and just put that in front of the UV. That's what I mean by the names need to match. It's UV and then whatever it happens to be. If I needed another UV channel for this object, I could do UV 2 underscore and then whatever it happened to be. So make sure you do that properly. And then we'll have to add some additional things as well later on. Next up, we need, let's see, next up is glossiness, metallic, and color. Those are just variables. You're all used to that already. You can safely ignore most of this stuff here. This is more advanced stuff about batching across your GPU. Let's just get rid of that for now. It's confusing, so let's get rid of it. Next up, we have example surf. Now, here it is. That input, which we defined here, this is all we're getting. Don't expect anything else unless you specifically state you want something else in here and you have that list that I gave you, or you can check out the Unity documentation. In, out, once again, it comes in, it has stuff, and it's also going to leave, which means that this is going to have values potentially in it. We're going to fill it with values. And when it leaves, it's going to use those values for further calculations later down the line. Inside of here, text 2D, main text. Well, we need to change that because that's going to be an error. We need to change this one too. So let's do example text, copy that to the sampler, make sure they're all the same name, make sure that's good. And then of course, this is wrong too. In dot, and this should be UV underscore and example text. If you do not remember why we have different UV sets with the name of the texture attached to them, it's because Unity is pre-processing these textures, the UV coordinates for us. So if we come over here and we create just any material, just a basic one right here, notice that you have these tiling offsets for certain parts. Most of these you don't, but for like emission or secondary maps, you have tiling. These are matrices that are going to scale up or offset your value, your texture, okay? Unity is going to multiply this specific part, that is the normal map, secondary normal map's name, and we can find the name if we go to select shader. We come down here and we look for something that's probably going to be there. There's detail normal map scale, which is probably what it is. That is going to be a separate value passed in, and it's manipulating only, it's only affecting that particular texture. Therefore, I need a separate set of UVs for each one. All the UVs are the same for the object when they come in, but because each texture is tiling over them differently, what Unity does is it applies each of those different tilings and it gives you multiple UV sets at that point, one for each of the textures that you provide. If you don't want that functionality, you don't have to use it. Once you have at least one coming in, I can use UV underscore example text to access other textures. Okay, just realize that I will not be able to scale the other textures differently. Okay, most of the time you don't want to do that. It's just in certain circumstances where that's a nice little added benefit. An important feature here too, at the end of text 2D, you have a multiplier by color. That you're going to see this commonly everywhere. Remember, color is multiplication. Okay, it's not addition, it's multiplying values. Okay, there are 0 to 1 ranges. Multiply black against white, all zeros by all ones. What happens? Turns to all zeros, okay? That's what happens when you multiply the colors. You multiply gray by white. What happens? You bring white from 111 to 0.5 for all the components, except usually for alpha. Usually they're going to be both ones in those cases, but they're all multiplied by component, and that's how you figure those things out. Many times in the things you create, you're going to want highlights, features, selections. You're going to want to change individually the color of each object. And this color property here allows you to do that without messing with the texture, right? So this, this cylinder here, now unfortunately they're all sharing the same material, so this isn't going to quite work the way I want to. But if I were to run it, it would. But if I come over here and I manipulate that particular material, you can see that I can make changes to it beyond the original texture there. What I really wanted to show you is that if I hit run right now, materials are a little bit more complicated. What happens is that each of these objects actually gets a separate instance of a material that you can access and work with. And even running this right now, it's not going to do what I want to, because they're using what's called a shared material. Because when you're working in the editor, you're working with lots of objects. And imagine if every object had a separate material. If you were trying to colorize individual brick walls, right? You got thousands of brick walls. Going through and manipulating each one individually, if you made a change to the color, maybe you wanted them a little bit darker, would suck. Flat out, horrible suck. So instead, Unity uses what's called a shared material. Okay, so that means all objects right now are sharing it. But at runtime, when you actually run this program, separate instances of each one are generated and created, and each one can be manipulated independently of all the other ones. Okay, that's why if I was actually if I built a game out and ran this, I could write a script that would grab this object's specific material. All right, and then I could change that material's specific color value so that only that one would turn a bright green when looked at, as opposed to the other ones which wouldn't be. Okay, and that's one way of modifying the appearance of an object to give you functionality, or to inform the player intent that they want to do something. Okay, so we went over the surface shader, and I hope you saw that it's very familiar to what you did before. The only difference is it's kind of like rolling everything about the vertex in the fragment shader into one, and you don't have to deal with the hard stuff like understanding that you need to convert coordinates from one place to another and so forth and so on. You fill in the blanks, the values here in terms of surface output standard. As you can see here, you fill in whatever values you want to calculate. You leave the other ones blank if you don't want to, and you send it off to the pipeline to be figured out later on. So let's go ahead and create something very simple. Let's talk about the diffuse color. So here is a very simple example where we're removing just about all of the properties. We're stripping this shader down to practically nothing. And in this case, we are going to use the standard lighting model. We still have our surface function. Even though we're not using it, I know we're not using it. Why do you have to have some kind of input? You always have to have something. So we're just leaving the default UV underscore main text. And in this particular case, we'll just have a color swatch come in, and we'll specify that the albedo, the output color, is what that color swatch should actually be. So if we wanted to do that, we could go to our example shader, and actually, you know what, let's do a shader. Let's do another surface shader, and let's just call this diffuse shader. And we will create a new material as well, and we'll do this diffuse. Now, this is not how you would want to actually implement this. You would want, when we get a few weeks from today, you are going to have different assets that have different names. This capsule is probably going to be different than this capsule in some way. All right, maybe this is actually a character. This is Bob and this is Alex, right? Alex is probably going to have a material called Alex underscore material or underscore M or whatever convention you want to use. The materials will not have the name of the shader. This is just for you right now learning shaders. You don't do it this way because what's the point? You have a shader slot right here that you can choose whatever you want to, right? Why would you name it the same thing that you have a choice of? It doesn't make any sense. So don't do that when you actually get to making things. So I'm going to go put a diffuse material on that. I chose the diffuse shader for that object. We can double click the diffuse shader, open that up, and let's strip this thing down. We're going to get rid of all those properties. Don't want them. Just going to keep the color. Once again, we'll keep going down. We are going to take in UVs. We're going to trash the rest of this stuff. We're going to trash everything except for the color. We want to get the most basic thing we can possibly work with so we know what we're doing. And then finally, down here is where there's a problem. We have a texture being sampled. We don't have a texture anymore. This stuff doesn't matter. All we have is that color that comes in for our object, right? And all we need to make sure we do with the surface function is if we want a color to show up on the screen, we need to make sure that the O.albedo value gets that color value. So here, albedo is a vector 3, a 3-component value, float 3 actually. So here we do C.RGB. RGB, of course, swizzling. We talked about that a long time ago, but make sure it's there. You could also use, STPQ, or you could use RGB or XYZW and so forth and so on. Let's just use RGB because we're dealing with colors, and that lets us know we're working with color values. We don't need metallic and we don't need smoothness, so they're gone. And the alpha value we do need to populate, and once again, we can just take that from the color value. Now, let's make George look like an idiot, and let's, of course, have a compilation error after we did that, and we don't. And importantly is, notice that we got rid of those parameters. They're still being passed in the pipeline, but the default value is being used. So the default value for smoothness or metallic, for instance, are 0. Therefore, this becomes a diffuse, fully diffuse object. If we select this other one with the other shader on board, and we come down here and we actually crank up the metallic or the smoothness, you can clearly see the difference now where this one is calculating, taking in that smoothness value. Now, if we crank everything down, they're going to look very much the same. They look a little bit different because of where the light source is pointed. But otherwise, the specular highlights are the same. Everything's the same because it's using the default values. And this was a huge issue many of you had on the homework assignments where you had variables declared, but maybe you weren't filling them with the right data, and you are getting default values coming down the pipeline. And that's one of the main reasons why I always tell you when I'm working with you one-on-one, don't use pure black, pure white. Don't use certain colors. Use something that you would never see naturally, right? That's why, yellows, crazy greens, or I tell you to put an R or a flat blue on there, because those are not standard colors you're going to see defaulting in the pipeline. Those are specific colors, okay? So always use them when you're debugging stuff so you know things are working properly. Okay, so we've stripped the shader down now to its bare bones, and we kind of know what's going on. So let's take a look at a few other interesting things. Let's talk about normal maps, because this is going to be something you're going to be using a lot in your projects. Normal maps are used to approximate what the surface would look like if you had a lot more vertices on it. However, you don't. The idea is that we're not trying to have very heavy vertex-laden geometry, because that takes more processing. Instead, if we have a light model, but we can encode that information into something like a texture, which is a good storage space. Well, one, it's good because it's not three-dimensional. It's already a dimension smaller than vertex data, right? A texture should naturally be smaller in most circumstances, and we can get a lot higher resolution for the same bang for the same buck, right? Or excuse me, a bigger bang for the same buck. That's the right phrase. So the idea is that we can have a flat two-dimensional surface that has a huge number of pixels, but if we were to try to encode what the values of each of those pixels were into vertices, we have a stupidly large three-dimensional object. The higher the resolution your texture, or the more pixels per polygon, the better your lighting will appear. Now, if that should be one of those intuitive things that you understand, okay? If we have, let's go with yellow because that's obscene. If we have a polygon, right, we'll make this triangle right here, and it's sampling the texture space, remember, 0 and 1 going up from here to here, and you have a 128 by 128 pixel image, that means half of these pixels, assuming this was truly going from 0 to 1, it's like covering half the thing, half of these 128 by 128 pixels are here, right? However, if you used a 512 by a 512 picture, intuitively, that's a lot more pixels. Just multiply those two numbers. You still have half of 512 by 512 now being used. So that's how same UV coordinates, same texture, but by the texture, excuse me, but larger texture. By the texture being larger, you fit more individual pixels into the UV space, okay? And that makes the object look prettier and nicer than before. So the idea is normal maps, we're going to, instead of specifying colors on the surface, we're instead going to encode within the RGB values. And actually, that's kind of a misnomer in and of itself these days. It's not quite the same, but the early days, the idea was we were encoding in the 8-bit of the R channel a X vector coming off to the side, and then the G value would be the Y vector coming off, and then the Z value is the Z out of the surface. And there's a reason why I'm having Z come out of the surface, and you'll find out in just a second. Normal maps are wonderful. They've been around. They were really popularized in Doom
Yo,
3.
Michael, can you mute yourself?
They're really pushed by John Carmack on the Doom 3 engine. They've been in literature, they've been used, and also other types of normal maps were used. They're called bump maps, and that's a huge naming convention. Remember how I told you how there's big naming problems in computer graphics, like with everything. But the idea is that they've been around for a while, and they're in all games these days, and they're used extensively to add additional detail, but they're false. If you look at the side of my cake, these walnuts, or whatever they are on the surface, if you looked at it from the side, you would actually expect it to look something like this. However, because it's just superimposed data on the surface, you don't get to see any of this stuff. It's like the people who talk about all of us in 3 dimensions actually living on a 2-dimensional shell of a black hole, if you follow theoretical physics, right? Where it's supposed to be 3-dimensional information, but we've encoded onto a 2D surface. And as soon as you see that surface from a grazing angle on its side, you realize the illusion breaks down, and you can tell it's not this grainy walnut pattern that you're working with, okay? There are other techniques out there, displacement mapping or height mapping and a few other ones, and they all have their benefits and their faults and so forth. But normal maps has been around a while, and they're probably not going anywhere either. So that's the thing. The important thing to note is we're not going to talk about in this lecture today how to create normal maps. That's coming in later in the pipeline when we develop things. What you typically do is you either have a higher resolution map and you project it onto the lower resolution surface, which is not without fault, mind you, there are problems. And then you also have lots of image processing algorithms. In fact, there are free ones. There's one called MindText that I own through Steam that I bought a long time ago. Photoshop had one, but Substance Painter, Alchemist, Designer, all those will have this built in. So you don't need to search for them like I had to a long time ago. You'll be able to do it automatically. You can also have what's called a height map. If you've ever worked with an Xbox Kinect, you'll know that you had height data. In fact, you had depth data. Well, depth data, so long as you consider it vertical instead of going into the scene, is the same as height map in a sense, right? It's telling you how close something is or how far out it should perturb. You can use that information to also generate normal maps as well. Normal maps are always going to look like this. And maybe if you ever dove into a game on Steam and opened up the textures or extracted them, I don't know about you, but this is stuff I did when I was your age and earlier. I'm even doing it now. My kids are invested in the SCP games, but they have very adult language in them, and my kids are 5 and 8, so I can't have them listening to that. So I rip apart the game, tear out the assets, and then replace them with their own audio recordings, right? But if you've ever done this stuff and you see maps like this, you're probably like, what is this? I mean, obviously this is a rock surface, right? But what is all this junk here, and why is it blue? Why is it so blue? Well, as with everything, there's a darn good reason for it. The bluish hint is based upon how the data is stored, what channel it's stored in. And more importantly, it's stored in a way that allows you to represent a vector that can go in both the positive direction and the negative direction. And that's super important for why it turns blue, and it's not just like a flat black or a flat really bright blue. It's right in the middle, and there's a good reason. We're going to get to that now, I promise. If you remember, one of the things that I harp on from the very beginning, and I say this a lot, is XYZ is RGB, right? Lock those colors in your mind. X is red, Y is green, Z is blue. Every application, every program, regardless of the coordinate system being used, adheres to that convention. And anyone who doesn't is crazy. That's the fact. Normal maps use what's called tangent space. So if you're interested in this, you can go real deep down a rabbit hole and read about how these things are calculated. All I'm going to tell you is you have object space, which is really great when you have an object, but normals are about lighting on the surface. So what we care about is not the entire object. We care about each individual face, okay? And because of that, each face has its own little coordinate system, if you want to think about it, but we call it tangent space. And we move from object space to this per face version here, okay? What you need to know about that is that the Z direction is the normal coming out of the surface, okay? So that is the value that's perpendicular to the surface coming out of it. So I said Z and B are linked, right? So already the fact that the normal of the surface is always pointing outwards means our Z value should, by default, be 1. Okay, so at this point, you should be saying to yourself, okay, my normal value, if I'm considering this surface, not world space, not local space, but if I'm on this face right here, right, always, my normal, always, my surface normal, always points straight out on the Z value. So Z is always a 1 in this case. So if we just casually think about that, we would be like, oh, okay, well then, why isn't this super blue? Why is this color that I'm showing here not the fully saturated blue, like if we went to the pointer options and I don't even get a fully saturated blue. Let's just pick something closer to this, I guess. Why is it not more like this than this other one? Well, because we need to represent the entire range of potential values, right? Because a vector fits on a unit circle, right? When it's normalized, it can be any value all the way around this, but in three-dimensional space. It's a sphere actually with three-dimensional graphics. So when we encode this value into this space, we also need to deal with negatives. Now, if we're dealing with old school stuff, we don't have floating point values, we have integer values, right? Between 0 and 255. So how do we get this to fit? And more importantly, how does your Windows operating system interpret the data stored in that and display it on your screen? So it's going to look at this image, right? The values, these vectors stored in these color channels. And what happens here is that for a value pointing straight out over here, right, or a value straight in here or up on this side, half of the data set has to be on the positive side, and half of our values for our integers has to be on the negative side to have both of these available to us if we want to invert it to the other way. All right. Therefore, a value pointing straight up does not start at 0, 0, 1, but instead it starts halfway. Would start at 0.5, 0.5, and then 1. Okay? That's how you get this color. 0.5, 0.5, 1 is equivalent to 128, 128, 256 if you convert it over to 255. There's 256 values, but only goes up to 255. That is how you get this color that you see everywhere. It's about taking the data, putting it into a different range through a function, and mapping it so that we can have all values. Now, I will tell you this right now, many engines disregard the Z component because the idea is that, okay, Z is always pointing out, and there's so very few limited cases where you want it to be pointing in, they will throw away the Z coordinate completely and use it to store other data, like the smoothness or the glossiness data, to make the texture size smaller so they can fit more content in. A game that I know does this is X-Plane. If you've ever played it through our FAA projects, I had to figure out the entire pipeline. They shove the glossiness, I believe, that's what it's called, but it's not technically glossiness if I remember right. But they shove that data into that channel because in theory, the Z value is always straight out. You never have to worry about it being flipped. It's useless, it's redundant, fill it with something important instead. Okay, so as I mentioned before, or maybe I didn't mention this, normal maps are actually a subtype of a thing called bump maps. And if you look up bump maps, you're going to find lots of different strategies. And I told you that normal maps deal with tangent space, and that's important. Bump maps can deal with world space, local space, different kinds of spaces. Some of them work with static objects, some of them work with non-static objects, and that's why I'm trying to warn you right now is if you start looking up normal maps, but you find stuff talking about bump maps in these other spaces, you're in the wrong place, okay? So back out of there and go back to looking up normals and tangents specifically. Why do other types exist? Because it's actually a lot cheaper to encode things in local or world space if you know an object is never going to move. You don't have to do matrix multiplications to move it from that space to tangent space. And there's actually some implications that we haven't discussed that are beyond the scope of this class, which is how do you define tangent space? Because I told you that the Z vector is always coming straight out. But if I have one vector locked and two other vectors, right, that are perpendicular, I can rotate these vectors 360 degrees all the way around, however I want to. I need something else to lock down that specific coordinate system, right? The IJKs, your vectors, right? Your IJK values if you're in physics. You need something else to lock it down. And if you want to know a hint, it actually has to do with the UV coordinates and how they're laid out on your object. And all that can have implications. But once again, this is the stuff that's a second year, third year type course, not for right now. Another really important thing, OpenGL and DirectX have different ways of storing normal data. Literally, the vectors are pointed in different directions. A OpenGL normal map will look different from a DirectX normal map. Unity uses OpenGL's method. This will only matter when we get into Substance Painter, but it will also matter if you start taking assets and experimenting with things online and you're wondering why, for instance, you have strange artifacts on the seams. It's because at a seam where I told you it has something to do with UVs, right? I gave you a hint. Well, at the seam of UVs where there's a split, the tangent vectors are flipped. So the lighting looks nasty because it goes from thinking the lighting is coming out to the lighting going in if you're using the wrong one. So if you notice these artifacts, flipped lighting, or just things seemingly being a little wrong, you might be using the wrong type of normal map, and it's an easy process to convert them. Most programs can do it. You can also specify that an object should be a normal map type by using the attribute normal when you're defining it as a property. Why is this important? Because when you get to normal maps, it has to be in the right format for several reasons. One of them I mentioned down here. I brought this up in the last class, I believe, or the class before it. sRGB, gamma, and taking color spaces and moving them from one space to another. Since normal data is data, it's not color information, it's not being used to actually display colors on a monitor, we don't want it to be, its range to be reformatted, okay? We want it to stay as pure data. Therefore, telling it that it's a normal, this is why. You have a slot, you specify that it's not a normal texture. You just say, oh, it's supposed to be a normal texture, but I'm not using this attribute right here. Some careless student drags their texture that is a normal texture, but it's not set to normal, okay? Into that slot, and it automatically gets this sRGB thing modified to it, and all the values and everything gets all screwed up and messed up, and nothing looks quite the same way that it looks in other programs that you're working on, okay? What this does is when you drag and drop that texture in, Unity checks the type that you dragged in. And if it's not a normal type, it will give you a pop-up that then says, hey, are you sure you want to do this? I can convert this to a normal map if that's what you meant. And then you hit yes, and it will convert the type to a normal map, and then you're good to go. This happens all over the time. There's an entire project over the summer where all the textures were incorrectly labeled as normal maps, and I was wondering why the hell everything looked terrible. And that was the issue. Everything was not set up properly. And at first you might not notice it, but you'll get an eye for these things and you'll see where things are really wrong at times. Okay, so we can manipulate the normal to enhance or subdue the effect as well. So the normal map that's incoming is just data. It's just a vector. You can perturb a vector however you want to. Add another vector to a vector, right? And you do vector addition, and now you got a vector going from here to here, and it's slightly off on the angle. Or if you take into consideration the slight perturbation, whatever you want to call it, however much it's moved over to the X and the Y, that's why the normal map isn't blue everywhere. What you're doing is you're specifying, okay, if the normal is coming out this way, the X vector is saying, okay, for this pixel over here, this surface has a little wrinkle in it on the high quality version. So I actually want this to be facing a little bit on this side, and this one a little bit this way and that way and this way. And so what you have are greens and reds coming into play on the map, because those are the vectors, those are the X and the Y values that you're distorting the vector a little bit on. And that's why you get the color ranges you do across the surface. But what we can do is if you take in a floating point scalar value and you multiply it by just the X and the Y component, okay, you'll end up with a larger value here, but the same Z size, okay? You add all three components back together, or whatever in your head, you can think of it as adding, but it's really just remaining the same thing. What happens when you make these ones bigger? It's no longer a unit vector, right? Instead, when you bring it all together, it's much larger. So then you normalize the vector back down to 1. And what happens now is the Z component is lessened and the other components are much larger. So it becomes far more biased towards the other components, is what I'm trying to say. And it makes the shading more pronounced. And you can do the opposite. If someone gives you a bad normal map, which happens a lot, you can put in a lower value like 0.5 and try to recover the subtler, softer surface details instead of having these really nasty, jaggy lumps all over the place. So let's see, hold on a second. Let's discard my annotations. I don't need them. So let's actually do this really quick. So let's see, I've shown you that as well. We're going to have you generate your own normal map soon, but what I want to do is show you, what time is it? We got just enough time to do this. I want to get you primed for what we're going to start doing as soon as this midterm is over. So you're excited for it to be over. You want to get it done. Let's open up Substance Painter, or is that Designer? I can never tell. Oh, Painter, good. They changed all the logos when Adobe bought them out, and it takes me a minute to remember which one's which. So I just want to take a second and show you how something like this is going to be created. We're going to use an existing model I've already done. You'll be following a very similar pipeline in the future. So of course, Mr. Demigorgon as well. Let's get this up open right here. And what's important here is that in this program, you manipulate all of the things we talked about tonight. The base color, the albedo as it's called, the height, roughness, metallic, and each of these are different channels, and I can cycle through them using hotkeys and so forth to show you all the data that's actually being painted and you have full control. This is what makes this program so much better than Photoshop. Photoshop's a pain in the butt to paint on individual channels and layers. In this, I paint on each channel however I want to. It's a ton of control, and it requires you to be responsible and properly do the right things. But here we can see the normal map that gets generated from the surface. And what it's doing is I took a higher quality version of this object with much more detail, much more richness, and I projected it onto the surface. And that's what we see if I hit, let's see, B. Let's go down to, let's curvature, position, thickness, normal. Actually, I didn't capture the normal data for some reason. Let me see why I didn't. Probably, so I removed it down here and I probably attached it manually. This is all advanced stuff that you probably don't need to know about, but the process would be, I would come in here and I would say, hey, I have a high quality model. Here is Demogorgon head high quality version. It would then shoot out rays from the lower quality one into the high quality one, sample the direction of that surface, and then encode that onto the pixel on the surface that you see here. And then you would end up with something that looks kind of like, let's go with this right here, okay? Now this also has additional normal information from this huge stack of textures you see over here, or materials as they're actually called on the side. This is a slightly more advanced, you probably won't get this far in this class in terms of the number of layers and setting everything up. What's important now is we go to File, we go to Export Textures, and then you will choose what textures you would like to export. Now, I've created my own Roblox pipeline because that's what I was making this for my kids, but normally you would choose something that's Unity compatible. So you would come over here, and it has built-in ones, and a lot ones that aren't, you won't have in yours. These are ones that I've made specifically for other projects that we work on. But we would pick something like Unity 5 Standard Metallic, and you could push that out. So let's go ahead and do that. And what you'll notice is there's metallic, albedo, normal, emission, height, and so forth. That's all good. Let's use that pipeline. I will grab Unity 5, and let's just do standard metallic copy, or yeah, we'll do that. And this is all good. You don't need to worry about it, what any of this stuff means yet. It's not your time. And we will export these out to, let's say, our desktop. And I'm going to specifically put these in the asset folder under shader examples. And I will put Demogorgon. And we will put our textures inside of there. And I will hit export. And it will then go through and actually export out all the different maps. How this does, how you do all this stuff will be covered in an entire lecture. So don't worry, you will be doing all of this yourself as well. Now that we have done all of that nonsense, we now have some data we can work with. So let's see, let's go ahead and come over here. So we have our Demogorgon area. We still need the object. So I'm going to go ahead and import an example object right here. And you know what? I'll throw up tonight, or if you optionally want a homework assignment, I will give you the normal map and a model to work with. I'll either make something or give you something new or something old. And you'll get all that, so you don't have to worry about creating any of this stuff. Let's go to, where's the model located? Let's see, we want to do Roblox and Maya, exports, birthday room, and Demogorgon head. Let's do that. Okay. Now we have a model. We can drag this into our scene. It's going to be way too small because Roblox and Unity scales are vastly different. And we will come here and we'll just artificially inflate the scale of this object up so that it's comparable to what we're working with on these other objects. And there we go. There's our Demogorgon model brought in. And now we can create our material, which we have not there. We will just create a new material and Demogorgon_M. We will drag that to the Demogorgon. And then now we will drag the correct materials to the correct slots. So that's where naming becomes a priority. Head, albedo transparent goes to the albedo slot. This is height information that shouldn't actually have not come for the ride. We're not going to deal with height. We have metallic and smoothness. Let's see. So we have metallic. And you'll notice that it gives you an option. Where does the metallic come from? Here, I'm saying it's stored within the alpha channel. And then we have our normal map, which I'll drag here. And you'll notice this is the error I was warning you about. This texture is not marked as a normal map. So if you selected the texture and let's see, texture here, you'll notice that texture type is set to default. We want to go to normal map type instead. Hit apply. We can go back to the material now, and you'll notice that the fuss is all gone because it knows that it's a normal map. It knows how to take it, convert it to what's called, I think it's M dot something DirectX format that Unity uses to encode normal maps into a floating point representation. Just throwing that out there for those of you who want to know what the heck's going on. And you'll notice now that with this standard shader, the normal one, normal, I don't want to use that word, but I'm talking about normal maps, you'll notice that we have interesting lighting effects that are beyond the normal detail that we had in that model beforehand, okay? That's what it's doing for us. So let's now implement something like this ourselves. So let's right click, go to create, go to shader. Let's go ahead and do a standard surface shader, and let's just call this enhanced normal map. And I'm going to try to keep all of those different channels as well. We'll see if I can do this on the fly and remember everything. So we have color, main text, glossiness, and metallic. So what we also are going to want is going to be a normal map associated with this as well. And of course we can do normal, and then we probably want to add that attribute. And I'm trying to remember off the top of my head, because this is one of the things where you write it once and you never remember. Okay, it is just normal. Normal, it's a normal map. And then what we want is it's a 2D texture. And if I remember right, there is a special normal type we can use for this. And if not, we can just use white or black or red. Those are all options as well. Okay, we're not going to worry about transparency on this object. Opaque's fine. We're going to use the standard model as before. Now what we want though is, right now we're only sampling the UV main texture coordinates. We are going to be doing a normal map work on this, so we're going to actually need a couple additional values to make that work. And actually, we're going to go back to the slides in just a second to show how that works once we get everything set up properly on this end. So what we're going to do is we're going to extract, all that stuff works fine. We've got a color value, color variable. Let's go back over here and set it up so that the Demogorgon material now doesn't use standard. Instead, it's going to use the enhanced normal shader. There you go. You can see that the support for the normal map has disappeared. We do have a slot for it. Let's drag and drop that slot in there, but once again, it's not being read or worked with in any way. That's up to us to do. We're also missing textures for smoothness and metallic. And if we want to add those features, you know what, we'll cover that in another video. We're already getting late into the class. Let's cover the normal stuff instead and get that over with. So coming back over here, first, we are going to define the normal map. We did that. We need the sampler 2D. I did not do that, so we need to go back and do that. This is the important part. We need to unpack the normal. Like I said before, the normal needs to be evaluated in tangent space. That is not hard, but Unity does it for you automatically. And there's no reason for us to look at the matrices and move them from one space to the other and figure all that junk out, okay? We can just call unpack normal, and what it requires is the raw normal taken from the texture. So we're going to use the text2D function to query the normal texture. Then we're going to use the UV coordinates for the normal texture to do that. And then we are going to plug the normal that we get out of unpack normal into the normal slot for the output. All right. So let's go ahead and set a few of these things up. So coming back over here, we have our normal map normal. We can copy that name if it makes it easier. Come down here and we can do a sampler 2D node, and we can do underscore normal. Now I have 2 underscores. Now we've got that set up. Down here, if we wanted to, we could, if we had, if we think we're going to have a need for separate UV coordinates, we could do UV underscore normal over here, so that if we had matrices or offsets being applied to that specific texture channel, they would show up in this UV set as opposed to using UV underscore main. Coming down here, we grab the color value. Now we need to do instead the vector value retrieved from it. So we need to do a text 2D like before, but we need to do this time, we're going to do underscore, and we're going to do underscore normal. That's the texture, the sampler 2D we're working with, but now we need the UVs. We need in dot, once again, in is the input struct up here, in dot, and we need UV underscore normal. And that's the normal UVs if we manipulated them in some way. Okay, that's just retrieving the value. We then need to unpack the normal using the Unity provided function to do so. So that's there as well. And then we need to store the value, and I always forget, I think it's a float point value we get. Yes, a float 3. So we'll come back here and we will do a float 3, and then we can just say normal is equal to that value right there. And now we just need to plug this value in. So let's do o.normal is going to be equal to, we will say it's just equal to our normal value. Let's see if that at least brings back normal map support for our object. And there we go. Now let's enhance that object or unenhance how severe it is, because that's pretty nasty in some spots. And the fact that the resolution of the texture is so low, we can clearly see the jaggies presenting themselves all over the object. Although it might look kind of nice from, I mean, that's not so bad. Anyway, so let's enhance this object a bit. So coming down here, we need to, so we've pulled out the data here. However, we want to enhance it before we unpack it. We don't want to enhance it after it's been unpacked. We want to deal with the value as it's stored beforehand. Therefore, we're going to have to split this line up into two separate lines where we're going to grab the texture 2D information first. So we'll do a float 3, or I mean technically float 4. I mean it could, it's a 4-channel texture, so we'll have 4 pieces of data to it. So we grab that information, and now we need to perturb the non-z dimensions. So we can do, and I did float 4. Let's call this something. Let's just call this temp is equal to that. We can do temp dot x, and we can multiply that by some scalar value. Let's put a range slider in here. So coming up to properties, we can do a enhance normal and modify normal intensity. And then what we can do is just do a range, and then we will, let's do -2 to +2, just because, why not? And we can set this to 0.0, so it will have no bearing on, it won't do anything to it at first. So we have enhanced normal. This is going to be a float value. I did specify a range, yes. So coming back down here, we can do a float and enhance normal. Coming down into our surface shader, we can now use enhanced normal to multiply the existing x component by that. And then we can do temp.y times equals underscore enhance normal. And actually, I'm interested in seeing if this is going to work. Let's try this. I think it will. Swizzling is pretty good. So I'm going to do times equals enhanced normal by the x and the y component, which will then get stored into. I don't know if you can do this. We'll find out together. So enhanced normal happens here. This value now, temp, is going to be passed into unpack normal, where it will then be worked with. It will then calculate the normal value, and it will get passed on further on into the shader stages, which we don't care about. All right, so there it is right there. So we set it at 0. So 0 multiplied by the x and the y vectors is, of course, going to destroy those components. Therefore, we would want this to actually probably be a value of what? 1. And there we go. We've got our original Demogorgon. So really, we'd probably want between 1 and 0 and +2. But here you can see we're really pushing it so that those intensities are way over the top, much further than they need to be. And then we can invert it by going the other way in this case. Now, let's see. What I think I need to do is let us normalize the vector afterwards and see if that causes any differences. So let's do temp is going to be equal to normalize temp. And come back over here. Okay. No, it doesn't. Yeah, I thought so. So the normalization happens already. You don't need to pass it in. But anyway, that's a way where if you have crap artists who aren't giving you good stuff and you need to do something in software and post, you can still manipulate these things in the shader to get a better quality than you had before. Okay, so where are we and what time is it? Because I know we're running out of time. These lectures are much shorter than my old ones, but for some reason they take much longer. So we did enhancing the normal maps. So here are 2 videos. Of course, you're not going to see them on the PowerPoint, the PDFs, but at least here you can see this is if you used a wave. And if you use the enhanced stuff, what you can do is you can make the waves actually appear to be more like foam when they're coming out in the negative direction, and then positive, if they're going in the opposite direction, they appear more like what you'd expect water to look like. So it's kind of an interesting effect. And yeah, already talked about that. Don't need that. Transparency. This will probably be where we end tonight, I think, and because we don't have a lot of time. So this will be probably the cutoff for what you need to know for the midterm. Transparency, as we mentioned before, and I've really tried to say this over and over and over again to beat it into your skulls. It depends on order, and by putting it in the proper queue, it'll be rendered from back to front, or in some rendering circumstances, you can actually do front to back and you end up inverting how you blend things together. Instead of blending it one way, you do the one minus way instead, is the simplest way to put it. To properly do rendering, you need to set multiple tags within it to be set to transparent. So one, the render type needs to be set to transparent. You also need to set the queue to be in the appropriate time, which is when it's rendering from back to front, which is also transparent. And then finally, there's an ignore projector that is recommended by Unity to put on, but because projectors are pretty much not used most of the time, don't worry about it unless you do something that really requires them. Finally, none of this will do anything unless you do pound pragma surface with an optional parameter of alpha. You can choose any of these parameters here, and they're all going to have slightly different effects. We're not going to investigate all of them tonight. We're just going to look at two really fast and an example next up. Finally, typically with a transparent object, you don't want to render the back side of it. So you will also use the keyword cull back, which means any back-facing geometry, remove it, throw it away. This is an example of what happens when you use two different render modes. The object on the left is using auto. This is closer to the transparency we talked about before, where if you choose transparent as opposed to fade, what you get. Here you can see that even though these parts between, so these are, the way this texture is actually supposed to look is these are large gaps in the object poking through. The shininess on the surface is shiny regardless of how transparent or opaque it is. It's a big bright white spot. Over here we're using fade. And fade will change the lighting on the surface based upon how it interacts with the light, right? So here you can notice it's transparent around these parts, right? The light is supposed to pass through it. The lighting calculations are not performed there. Therefore, the specular highlight disappears in these locations. Whereas over here, it's more like a glass sphere or bauble or something, right? And that's why you still get that sheen on the outer surface. That's a very important characteristic when you're doing things like there's an old game called Guild Wars. It was a free MMO, and they had used this effect all over the place for enhancements and shining things. Not the new one. I'm talking about the original one. And this, being able to choose one over the other is important to explain to the player what's going on in the game. One, it seems like you're encased in glass. The other one, you naturally understand that these are missing pieces. It's not a solid object that's transparent. So that being said, here's what you need to do. This is probably the most popular and sought after extension of the Unity surface shader. And that is, yes, I have transparency on a texture. However, I also need an object that already has transparency to fade in and out. So people could shoehorn this by directly manipulating in real time the texture and writing to the alpha channel and making it disappear, right? However, if you write a shader that has two alpha inputs, one alpha is going to be the, it's going to be the alpha from the texture, what truly should be missing from it, if you're doing electricity or some other effect, versus the fade alpha, which is where you're trying to get it to remove because maybe it's a weapon pickup or something else. You walk over it, it disappears, and you move on. That's the idea here. So we're going to implement this very, very quickly, and this will probably be the last thing we do tonight, given the time we have left. So, Mr. Demogorgon, you need to have some transparency to make this more interesting. So once again, to just show how easy it is to manipulate things, why don't we just go to start and open up Photoshop really fast, and I'm going to add some transparency randomly, or maybe not randomly, maybe we'll do it based upon some kind of color information or property of the surface. So we'll click and drag this over into Photoshop or whatever application you like. And once again, this looks like a giant mess, but you can see the parts here are the different, flaps, flesh flaps. Do we want to call it? That sounds horrible. There's the mouth over there and all the different parts. So let's go to select and we'll do a color range, and I'll pick a color like, what do I want to make? Let's make this weird whitish color disappear. So I'm going to select everything that's similar to white, and then I'm going to use that as a transparency, and I'm actually going to invert that so that only individual spots are kind of gone. And then what we can do is if we really want to play around with it, we could like blur it a little bit, and then we can use levels. You can go to town with all this stuff, do whatever you want to. Oh, let's see. Why is it? Oh, you know what? I'm using hotkeys and it's trying to kick. It actually almost closed the meeting on me there. That was not good. Okay, so that means I shouldn't use hotkeys. Anyway, coming back here, now we have transparency data embedded within the texture. I'm going to go ahead and save the texture, minimize this, come back into Unity, and let's just take a look at the Demogorgon. If we come over here, we can say that, yes, input texture alpha information, texture is transparency, hit apply. What you'll notice now is we can see in this preview window that segments are missing. That's why you clicked alpha's transparency, so you can see it here and understand how it's being used. But over here, of course, it's not working because we haven't done any of the things I said that are necessary to make something work in this pipeline. So render type, we need transparent, and this is also one of the most common things, errors, is to completely mistype transparency. Transparent, oh my gosh. I can't remember, is it transparent or transparency? Let's come back up really fast. And it should be transparent, yes, okay. So I was correct the first time. All right, so we did render type transparent, and now we need to do Q also equal to transparent. And I'm going to, I don't care about the ignore projector crap. We're not using it. It's not going to be something that we work with, so ignore it. Surface, surf, standard, full forward shadows. Technically a transparent object, shadows really shouldn't be something we deal with, but let's just do an alpha, and I want to do fade this time. Once again, we saw the reason why I would prefer fade over something else. So over here, we have our input from our texture. This is a fixed 4C, so we know we're getting the alpha because it's RGB, then A as the fourth channel. Here we've gotten the normal information, that's all fine. This is all good. And all we need to do now is we output the alpha into this. That is correct as well. Now the only thing, and I'm trying to see, let's jump back here and see if we get any errors. And there you can see a big problem right there, where I'm actually rendering parts of the back side of the object. Now, this is a bigger issue than you might believe. This is why transparency is a very pain in the ass topic when it comes to computer graphics, because all these little tiny weird effects come into place because you don't know the order of things being rendered, and the back can come before the front and vice versa. And we have to do a lot of steps to make sure that that doesn't happen. Ignore that for a second. What we are going to do is we are going to do a, let's do a call back really fast and come back to Unity. And yeah, no change. And that's, until we do something different, that's going to be the way it is. But importantly is transparency does work, although not in the way we want. And what I'm going to do is we're going to get back to this part of the slide. I actually want to jump ahead because I was using less complicated objects before. Let's get fade working really fast, and then I'll show you how to fix that issue with it being weird on the screen. So what we need now is we're going to add a underscore fade value, and let's just once again call it whatever, because we don't have time. And let's do another range, and this will be from 0 to 1, and this will be starting out at 0 to begin with. So fade, the idea is if fade is 1, it should be completely faded. If fade is 0, it's fully opaque. So remember what you call things, because that you might actually do it the opposite way, and it wouldn't be intuitive that a value of 1 would actually be fully opaque instead of the other way around. So let's come down here. We'll do a float fade. And once again, we have 2 floats here, so we could technically throw these all into a single vector and just have it using each component separately. But then you'd have to document that to make sure people understand what it is you're trying to do. So coming down here, what we can do is we have O.alpha is right now just equal to C.A. We also want to incorporate the fade value. You can do this in a couple different ways. We could do this the cheapo way, where we just multiply this by fade. But that's going to affect all of the object all of the time. Okay, so right now, here's my wonderful variable, whatever, and you'll notice it fading in and out. But importantly is that even the transparent parts are also being faded out. And if you have a transparent part multiplied by a value that's less than 1, which is what fade is, right? It becomes it becomes more transparent. So you're actually making the transparent parts grow by doing it this way. More different way of doing it that preserves, and I have a cat that's about to throw up behind me. You might be able to hear it. The better way of doing this is instead by first, you'll notice that fade is operating wrong. It's the opposite of what I want it to be. Fade at 1 should be fully gone. Now it's the opposite. Fade at 0 is fully gone. So by inverting that value, I am going to actually do 1 minus that. And what I also want to do is use the minimum value for that particular point being calculated. The reason is because minimum is the lower it is, the more transparent it is, right? And it's where it's going to disappear in my case. I always want to use the least value accessible to me. So it's going to respect the texture's opacity values. And then as fade encroaches on that, it will then transition over to using fade's value instead appropriately. So let's go ahead and do both of those really fast. So we will do fade 1 minus fade, correct? And then we can, of course, use a min function and make that happen, save it, move it back over here. And now it flipped because we inverted the value between 0 and 1, right? And now whatever operates properly. You know what? That's whatever's fine for a few moments for a giggle or a chuckle. But let's actually call this fade and come back over here, come back in here. Now it's actually called fade. So fade of 0, which intuitively makes sense, no fading is whatever it is. And then we fade it off into nothingness. All right, so now we have a great system for that. The last thing we're going to talk about tonight, last thing is just a slight extension to this and why it looks creepy and weird. Here's an example of a cup. The reason why the Demogorgon looks weird is because it has concave surfaces. They go inwards on the object, okay? So now you're rendering a front side, a back side, a front side, and a back side on top of each other, right? There's multiple sides going on with this object. To make sure that this renders somewhat appropriately, because true transparency isn't really possible, right? We're not doing ray tracing. We don't intercept the object. We don't sample it. We don't know what's going on as we pass through it. But to get it to look somewhat appropriate, what we can do is do a little trick. And this is going to be the first time you see passes. A pass will allow us to render the object, but not all of its information. In fact, we're not even going to render the color information. We're going to render it, but just its depth information. And what that means is the depth buffer now holds that object. And if we render it again, but this time render it the way we plan on doing it, remember the depth buffer is going to reject stuff that's behind it. So all those surfaces that are screwing things up, that are being rendered in the wrong order because it's a concave surface, it's going from front to back to front to back and front to back and so forth and so on, those will all be culled out because they're behind the values that were stored for depth. All right? That might sound confusing, but just it's a very easy thing to do. All we need to do is add this little bit of code at the top of our subshader. Remember, we talked about the fact that you can have multiple passes. We discussed these things so that you have them in the back of your heads, so that when I bring them up, hopefully you have at least a passing memory. So here, pass, Z-write on. That means in this pass, I want to write depth information. Color mask 0 means I don't want to write any color data whatsoever to the buffer. 0 literally means nothing. You could put an R, a G, a B, an R, a B, whatever order you want to, even alpha if you'd like to. And the cool thing is it will only render that contribution in that particular pass. We're using this simply to figure out what data to remove from the pass, all right? So we don't want any of that stuff gumming up the works. So instead, right here, all we have to do is include this little pass. So this pass happens, and then the rest of our code executes after that, all right? So let's come back over here and take a look at Demogorgon and bring it back, and you'll notice the effect works because it's doing a pre-render, figuring out which parts are in front of us, and it's throwing away all the trash that we don't need. And if I turn on my lighting, now you can see that there is actual transparency here along these seams, okay? Or here along the back. Now, there's an issue, of course. Where's the other side? We're seeing straight through it. And now you're starting to get into the area where, yeah, this is all trickery, okay? We're faking this, all right? We don't have real ray tracing. We're coming up with algorithms to make it work. And there are lots of transparency algorithms out there. All right. We're just covering some of the basics right now. So what we're not going to have on the exam, and we'll cover sometime later, or if you want to, you can cover this on your own. We are going to talk about how to create a gradient. More interestingly, at least to me, is how to do one procedurally through code, and how Unity has the capacity to do that, and how you can create interactive texture gradients and then apply them to materials at runtime if you want to. Then we were going to talk about how you could use height gradients to create shaders for terrains or other objects that would automatically map the gradient you created to create an automatically textured island instantaneously without any work that you actually have to do, which is pretty fun. And then, of course, an example of how we would have done that if you do it fully procedurally. This is what it ends up looking like, where you calculate different zones where it's green or yellow or so forth, and then you can have a tide rising and setting, however complicated you want it to be, basically. And the last thing we would have covered is creating your own custom lighting model. That is very complicated. I only make passing reference to it so that you know it's an option, but it's definitely not something that I would go into. And we use our own custom lighting model to create a toon shader for the Demogorgon, as you can see here. So instead of calculating these different values, the diffuse calculation, the dot product, is used to access the texture at different locations. So zeros down here, ones up here, so you can actually see that as you move across the surface, which ones become bright and which ones become dark instead. And then if you want to, we would have covered how to do your own CG include files, which means after you create a lot of code, how you can not compile it, but pull it all into one spot, put it in your Unity project to use on subsequent projects so you always have a database of stuff to work with. That being said, midterm next week, right, guys? Everyone, men, women, everyone, midterm next week. Bring your questions because we're going to have a review at the beginning. The way I see it is we probably won't have class for more than 30, 45 minutes unless you all ask a lot of questions. I'm going to look through all the PowerPoints. I'm not going to cover everything. I'm going to cover things that I know are important. You should still look at all the information, but the purpose for you coming to class next week is because I'm going to probably indicate somewhere between what 60 to 75% of the material on the exam is going to be by what I emphasize in that video. Class ends, the midterm is unlocked. For those of you who have some sort of exception for needing more time or specific locations, your midterm might take 5 or 10 minutes longer to unlock just because I have to do a few extra steps. But yours will have whatever necessary time allotments that you require in your specific midterm. It's the same midterm that everyone gets on Canvas. It's just yours goes through a slightly different process to get additional time. You will have, as mentioned, we'll talk about this next class. You'll have all week to finish it. It's due before class, though, not after. This isn't, you don't get help on it the following class, so it's due by 4:59 p.m. that day. You have to have it submitted, and that's a hard deadline. If you don't submit it by then, that's it. It's your midterm. You'll have to take the final exam to try to replace the grade. There is a Canvas portion, and then there's a small, not meant to be brutal, code portion as well. That being said, we're pretty much out of time, but if you have any questions that you wanted about the midterm that you want to ask now, feel free to. Otherwise, hold them till next week.
More of a general question, but when would you say you're most available in case we have questions? Just find to email you or something?
Yeah, just shoot me out an email. That seems to be what most people are preferring to do. And if something requires more hands-on, like one-on-one interaction, I can launch the same link that you have here, the WebEx Lecakes address, and invite you, and we can share screens and discuss whatever you need to if you have specifics. But especially during next week, while the midterm is actually due, feel free to contact me with questions about the midterm for the coding portion. I don't recommend you try to contact me unless there's something really wrong with the quiz portion on Canvas, because that is a timed segment and I don't want you to be stressing about time. the way I handle midterms, and I know I don't have much time, so I'm gonna say this really fast. The way I do it is I write the questions. I personally take the midterm, and I know, however, because I know the answers, obviously it's going to be fast, but I take into consideration how long it takes me to click through things and making sure it's all correct. I take that time and I usually multiply it by 3. And that's what I expect you would need if you had some idea of what the material is and you're able to work through it. Um, since since the midterm portion that's on Canvas is timed somewhat, it's a long time, but it's still timed. uh, you should not be looking through the notes for every single question. The idea is that you have some grasp of the material. You've picked it up by osmosis, whatever, and you're able to answer some of these questions. Well, maybe once in a while you need to check yourself. That's fine. That's why you have the extra minute or so on each question. But for the most part, you should be able to do this without needing any kind of notes. But you are free to have them. There are no restrictions. The coding portion, on the other hand, is where things are going to be more abstract and you have the full time to do it. I'm not going to make it crazy complicated or anything, but it's definitely going to be an assignment you will not find anywhere online. I will make sure that I use the data, the colors, and everything in weird, strange ways that are not typical, that you'll only find in this exam. Okay? Other than that, if you have questions, go ahead. Otherwise, everyone else, you're free to leave. Class is pretty much done. Have a good night, everyone. Deep, you have anything you wanted to go over really fast, or are you good?
Yes, Professor. Professor, wanted to ask you one question.
Sure.
Do you have any sample like exam or something like from the previous
No,
semester?
I would never give one out.
Oh, okay. So that okay, I definitely understand. I thought like if it is the distinct from the previous one, so I can have a practice of that thing. That's the reason. Neither it's okay.
The quizzes are your primer. That's why they exist. In previous years, when we had a face-to-face class, today I would have walked in and I would have given everyone a pop quiz with questions with that would have lasted 20 minutes with questions similar to the style of the exam. That's what the quizzes are this time. So you know the style of questions I wrote all of them. That's the kind of stuff I'm looking for. So that's what you can expect.
Okay. So definitely, I'll go back to all those quizzes and then go through. And
It's not going to
Professor,
be exactly the stuff on the quizzes, obviously, but
yeah, definitely.
that's the important information, right? So, tweak a definition here or tweak a number or variable here, and that's the kind of stuff you're going to see.
Yeah. Just wanted to ask you, like the polls would be on Canvas, right?
I'm sorry?
The polls for the homework homework 5 or
Yes, I need to do that. I have to walk away for like 15 minutes to get my kids to sleep,
yeah.
and then I will go on Canvas and do that. I need to figure out the best way to do that, whether that's an announcement. So you said you have done Canvas in the course you assist with, correct?
Yes.
Have you done one before? Do you know the best way
The
to do
po-
it?
we try to send out and everybody submits a 1 pointer homework or 0 pointer homework. We did
Oh my
that.
word. Okay. I'll see if there's another way. This sounds like a
I'm sorry
pain in
for
the
that.
ass.
Because last time we had to do that thing for our lab reports. Is the due date okay or not for that thing? And
Mhm.
we sent it out a 0 grade homework and everybody just mentioned it on that thing and then we evaluated that what
All
looks
right.
good bad.
I know there are some extensions that you can download. I'll see if there's anything like that. But I will
Yeah.
figure that out in the next
And
hour.
I was able to figure out that thing last time when I was trying to discuss about the tabs thing. So there is an activity log in each and every quiz if you look.
Ah, okay, good.
So over there you can see that what activities were done by that particular student during that time.
Okay, that's interesting to know.
Yeah. So yeah, no, thank you, Professor George. I hope I would be able to do some good in the midterms because I'm very scared about that thing right now.
Don't be. Don't be scared. Review the material. Next week, we're going to sit down. And like I said, I'm going to tell you what's important in the
Okay.
class. Don't be frightened about it, okay?
Okay, sure. And Professor, I just wanted to ask you one question. Like for the any homeworks in the further, right?
Yes.
would you mind providing just a screenshot of the output file? So like I'm not able to visualize what the output should be
Okay.
at the end of the whole code. Like after doing the whole program of the code and homework thing, sometimes I get confused saying that, okay, I'm doing correct or not at the end of the day.
Yeah, that's not a problem. But
So
there'll probably only be a no, yeah. You know what? I can totally do that. That's not a problem. I'll put a screenshot at the bottom of kind of my final expectation.
yeah, exactly. So like we can understand that, okay, this is what we need to achieve the target at to get some good grades at least. Yeah, okay, no worries. Thank you so much, Professor.
Yeah, no problem. Have a good night. I'll see you next
Yep,
week.
you too. Yep, see you. Bye bye.